Some discoveries don't rewrite history. They expose how little of it we truly understand. Across the ancient world, colossal monuments still stand exactly where they were placed thousands of years ago, surviving civilizations, empires, and even the landscapes that once surrounded them. We know they exist. We know roughly when they were built. Yet for many of them, the most astonishing questions remain unanswered. How did ancient builders shape, transport, and position stones that weigh more than modern construction equipment can easily handle? Why do sites separated by continents reveal engineering ideas that seem strikingly similar? Every expedition uncovers another clue, but the mystery only grows larger. Perhaps the greatest legacy of the ancient world is not the monuments themselves. It is the realization that humanity's past may be far more extraordinary than anything history books have been able to tell us. Konark Sun Temple, Odisha, India. Rising from India's eastern coast, this 13th century monument appears to be carved from stone, yet its true design suggests something far more extraordinary. Rather than functioning as a conventional temple, every major element seems to participate in a single mathematical system so precise that many researchers describe it as one of the greatest architectural expressions of astronomical knowledge ever created. Although local communities had never forgotten the site, much of the monument disappeared beneath drifting coastal sand and dense vegetation after centuries of abandonment. European travelers recorded its imposing ruins during the 16th and 17th centuries, and systematic archaeological documentation began under the Archaeological Survey of India in the 19th century, revealing that what survived was only a fraction of an original structure that had once dominated the Bay of Bengal. Even in its damaged state, the remaining architecture preserved enough geometric order to convince scholars that accuracy, rather than decoration alone, governed nearly every aspect of its construction. Built during the reign of King Narasimhadeva I of the Eastern Ganga dynasty around AD 1238 to 1250, the temple was conceived as the celestial chariot of Surya, the Hindu sun god. The surviving platform stretches roughly 100 meters across, while historical reconstructions suggest that the main sanctuary tower originally rose between 65 and 70 meters before collapsing centuries later. Yet the true mystery begins only after looking beyond its impressive dimensions. Every proportion, every carved wheel, every alignment, and every axis appears to belong to a single astronomical blueprint whose overall precision remains difficult to explain using only the surveying tools traditionally associated with the 13th century. The entire monument functions as an enormous astronomical machine, rather than a symbolic representation of one. 24 gigantic stone wheels line the sides of the platform, while 7 sculpted horses appear to pull the colossal chariot toward the east, reflecting the daily journey of the sun across the sky. At first glance, these seem like religious motifs, but closer examination reveals an astonishing numerical consistency. The 24 wheels correspond naturally with the 24 hours of a day, while each wheel contains 8 principal spokes that match the traditional Indian division of the day into 8 prahar, each lasting approximately 3 hours. Additional carvings divide those intervals into smaller units that may have been intended to represent even finer measurements of time. None of these relationships appear accidental because they repeat throughout the monument with remarkable consistency. This mathematical coherence becomes even more remarkable when sunlight is introduced into the equation. Researchers have demonstrated that several of the stone wheels function as highly accurate sundials. Standing nearly 3 meters in diameter, each wheel possesses carefully carved spokes and decorative ridges that cast predictable shadows as the sun moves across the sky. Experimental measurements conducted by archaeologists and engineers have shown that the changing shadows can indicate local solar time, with an accuracy often estimated within only a few minutes under favorable conditions. Such precision depends not merely on carving an attractive circle, but on calculating the orientation, spacing, spoke thickness, and shadow geometry with extraordinary care. The unanswered question is whether these wheels were intentionally engineered as scientific instruments from the very beginning, or whether their accuracy emerged as an unexpected consequence of architectural symmetry. Either possibility demands a sophisticated understanding of solar motion that exceeds what many people assume for medieval construction. That question becomes even harder to dismiss when the temple's overall orientation is considered. Konark faces almost exactly toward the east, and historical descriptions preserved in regional traditions suggest that the first rays of the rising sun once traveled through the entrance and illuminated the principal image of Surya inside the sanctum. Because the original tower no longer survives, the complete lighting effect cannot be reconstructed with absolute certainty. Yet computer modeling and archaeological analysis indicate that the alignment was almost certainly deliberate. Achieving such an effect would have required repeated observations of sunrise positions across the seasons, careful corrections for the local horizon, and a level of surveying capable of maintaining the temple's central axis across an enormous construction site. Even today, establishing comparable alignments for monumental buildings requires precise reference points and repeated verification. As researchers continued measuring the surviving structures, another pattern gradually emerged. The monument is not simply symmetrical in appearance, but geometrically disciplined throughout its design. Laser surveys and architectural studies reveal that opposing elements closely mirror one another despite centuries of structural collapse. The massive wheels are positioned at carefully repeated intervals. Decorative programs remain remarkably balanced across both sides of the platform, and the principal axes preserve consistent proportions over distances extending tens of meters. None of this guarantees mathematical perfection, yet the cumulative accuracy strongly suggests that the builders relied upon standardized measurement systems rather than visual estimation alone. Surprisingly little documentation survives describing exactly how those measurements were established, leaving historians to reconstruct the process only from the finished stonework itself. Such precision becomes even more impressive when considering the materials involved. Most of the monument was constructed from condylite stone, supported by laterite in the core, while chlorite was reserved for particularly intricate sculptures and door frames. Many individual blocks weigh several tons, yet their joints remain so closely fitted that thin blades can scarcely penetrate certain seams, even after nearly 8 centuries of weathering. Unlike modern reinforced concrete structures, the temple depended upon carefully shaped stone blocks, whose stability relied on accurate geometry instead of thick mortar layers. Every small error would have accumulated as construction progressed, making the consistency visible across the surviving platform especially difficult to explain. Hidden within those stone courses lies another engineering achievement that often receives less attention than the carvings themselves. Iron clamps and dowels were inserted to secure many structural blocks together, forming an internal framework that distributed enormous loads throughout the monument. Remarkably, numerous iron elements have survived despite centuries of exposure to humid marine air, only a short distance from the Bay of Bengal. Metallurgical analyses indicate relatively high phosphorus content and manufacturing techniques that improved corrosion resistance compared with ordinary wrought iron. Although researchers understand many aspects of this metallurgy, the exact production methods used by the medieval craftsmen remain incompletely documented, raising further questions about the technological capabilities available to the builders. No discussion of Konark would be complete without addressing the famous legend surrounding its supposed magnetic crown. According to long-standing tradition, An enormous lodestone once occupied the summit of the temple, allegedly powerful enough to suspend the central idol or interfere with the compasses of passing ships before Portuguese sailors removed it. Modern archaeology has uncovered no evidence supporting these dramatic claims, and no surviving structural remains indicate the presence of such a massive magnet. Nevertheless, the persistence of the story across multiple generations illustrates how unusual the monument appeared, even to later observers who struggled to explain its apparent sophistication. While the magnetic legend almost certainly belongs to folklore rather than science, its survival reflects the enduring impression that the temple embodied knowledge beyond ordinary expectations. A greater mystery is not how Konark was built, but why its towering main sanctuary disappeared, while much of its precisely aligned platform survived. Historians have proposed earthquakes, cyclones, lightning, structural failure, iconoclasm, and deliberate dismantling, yet none fully explains the evidence. Because the central tower collapsed long before modern archaeology began, the most important part of the monument's astronomical design was lost, leaving researchers to reconstruct its original purpose from the remarkably precise remains. The Temple of Hathor at Dendera, Egypt, preserves one of the most precisely organized visions of the ancient sky ever carved into stone. European scholars encountered the temple during Napoleon's Egyptian expedition, and in January 1799, artist and explorer Vivant Denon entered a rooftop chapel dedicated to Osiris and recorded an extraordinary circular ceiling. The relief was removed in 1821 and later transferred to the Louvre, while a plaster replica now occupies its original position. Yet the discovery revealed far more than an unusual religious image. It exposed an ancient attempt to compress the observable universe into a carefully ordered stone diagram whose astronomical meaning is still being debated. The circular Dendera zodiac measures roughly 2.5 meters across and was carved from blocks of sandstone fitted into the chapel ceiling. At its center, constellations, planets, and divine figures rotate around the northern region of the sky, while 12 human and falcon-headed beings support the celestial disk from the outside. Unlike most Egyptian astronomical ceilings, which arrange the heavens in long rectangular bands, this composition presents the sky as a circular planisphere. It includes the familiar zodiacal forms of Taurus, Leo, Scorpio, Capricorn, and Pisces, but combines them with older Egyptian figures, such as a hippopotamus goddess, a bull's foreleg, and deities associated with the northern stars. This fusion reveals that the designers were not simply copying a foreign zodiac. They were integrating Greek and Mesopotamian astronomical traditions into an Egyptian system of time, ritual, and cosmic renewal. Its precision becomes most remarkable when researchers attempt to determine what moment in the sky it may represent. The relief includes the 5 planets visible without telescopes: Mercury, Venus, Mars, Jupiter, and Saturn. Each appears through a divine figure placed close to the zodiacal constellation in which the planet may have been observed. Researchers have therefore compared the arrangement with reconstructed planetary positions from the late Ptolemaic period. The strongest interpretations place the represented sky near the middle of the 1st century BC, close to the reign of Cleopatra VII. 2 unusual circular symbols have also been interpreted as records of eclipses: a lunar eclipse on September 25, 52 BC, and a solar eclipse on March 7, 51 BC. These identifications remain interpretations rather than universally proven facts, because the accompanying inscriptions do not explicitly describe eclipses. Even so, the proposed dates fall remarkably close to the period in which the chapel was decorated, suggesting that the artists may have encoded real celestial events rather than creating a purely symbolic arrangement. That possibility changes the relief from a decorative horoscope into something far more sophisticated. Recording planetary positions requires repeated observations because the planets move at different apparent speeds against the stars. Mercury is often difficult to see because it remains close to the Sun, while Saturn takes approximately 29.5 years to complete one orbit as seen from Earth. A single observer could not easily establish the full pattern without inherited records. The Dendera zodiac may therefore represent the final product of observations accumulated by generations of temple astronomers. Although no surviving archive explains how their measurements were organized, they possessed no telescope and left no clearly identified instrument capable of plotting the entire sky. Yet they distinguished wandering planets from fixed stars, followed lunar cycles, divided the night into measurable periods, and preserved the results through a visual language precise enough to be compared with modern astronomical calculations. The mystery deepens because the zodiac was not isolated from the architecture around it. The main temple of Hathor formed part of a sacred complex covering tens of thousands of square meters, while the temple itself extended approximately 137 meters in length and 47 meters in width. Inscriptions preserve an unusually detailed construction chronology. The first stone of the inner sanctuary was laid on August 23, 237 BC. Decoration of its hypostyle section began in 212 BC and was completed around 206 BC, while the pronaos ceiling was finished in 124 BC. Other sections continued under later Ptolemaic and Roman rulers, and the temple was ultimately completed under the Roman Emperor Tiberius. Such dates show that Dendera was not produced through hurried improvisation. Its geometry, chambers, ritual routes, and ceiling programs were coordinated across several generations without losing the original architectural logic. Visitors entered through a monumental facade approximately 40 meters wide, supported by 6 enormous Hathor-headed columns. Beyond it stood a hypostyle hall whose ceiling was carried by 18 additional columns arranged in disciplined rows. Each capital displayed the face of Hathor on 4 sides, forcing sculptors to repeat the same proportions around massive stone supports while maintaining their alignment with the surrounding architecture. The ceiling above them was divided into astronomical bands showing stars, lunar phases, solar boats, and the elongated body of the sky goddess Nut. These images were positioned within a structural grid rather than added randomly after construction. Columns, roof slabs, and carved registers had to correspond so that architectural loads could be transferred downward without disrupting the visual sequence overhead. The surviving roof demonstrates how accurately that system worked. Heavy sandstone slabs span the spaces between columns and walls, yet large portions of the ceiling remain stable after more than 2,000 years. The builders had to control the height of each column, the level of the capitals, and the contact surfaces beneath the roof blocks. Even a small cumulative variation across a hall of this scale could have concentrated weight unevenly, cracked the stone, or distorted the astronomical scenes. Instead, the ceiling behaves as both a structural surface and a continuous map. Its survival does not prove the use of lost machinery, but it does reveal advanced surveying, standardized measurement, and highly controlled stone preparation. Dendera's builders also faced a more subtle challenge, transferring a celestial design onto a ceiling where normal visual judgment becomes difficult. Artists working on scaffolding could view only small sections at close range, yet the completed figures remain connected across adjoining blocks. Circular curves continue through separate stones, bands preserve consistent widths, and inscriptions remain balanced around astronomical figures. The full zodiac could not have been improvised one symbol at a time. Its geometry was almost certainly planned on a smaller scale before being enlarged through a grid or modular system, although no original drawing has survived. The unresolved question is how the planners converted observations of a curved sky into measured coordinates on a flat stone surface, while preserving both astronomical order and religious symbolism. This precision did not end with geometry. Recent cleaning revealed vivid blue, red, green, and yellow pigments beneath centuries of soot. The colors clarified details that had become nearly invisible and showed that the ceiling was conceived as a luminous cosmic environment rather than bare carved stone. Pigments had to be applied across enormous overhead surfaces while respecting thousands of engraved boundaries. Their survival reflects careful preparation of the sandstone and the use of mineral-based colors capable of enduring a dry but chemically demanding environment. Yet the exact organization of the workforce remains unknown. Stonecutters, painters, scribes, priests, and astronomical specialists must have coordinated their work, but no document records how many people participated or how technical corrections were communicated across generations. The Dendera zodiac remains the strongest evidence of that lost coordination. It is not a modern scientific chart, and its figures cannot be treated as exact points on a computerized star map. Religious meaning shaped every part of the design. Nevertheless, its creators placed recognizable constellations, wandering planets, and possible eclipse symbols within a coherent celestial system dated closely to the architecture surrounding it. They transformed decades of observation into a circular composition that still allows modern researchers to test proposed dates against the reconstructed sky. Guachimontones, in the volcanic highlands of Jalisco, Mexico, was built around a shape that ancient architects usually avoided: the perfect circle. For centuries, the grass-covered mounds above the modern town of Teuchitlan attracted little attention. Archaeologist Phil Weigand began documenting the wider region during the 1960s and 1970s, but systematic excavation and restoration expanded mainly in the late 20th century. What emerged from the soil was not a conventional Mesoamerican city of square plazas and straight-sided pyramids, but a ceremonial landscape organized around immense concentric rings. The people now associated with the Teuchitlan tradition occupied this region centuries before the rise of the Aztec Empire. At Guachimontones, they constructed circular patios, ring-shaped platforms, stepped conical monuments, and rectangular buildings arranged like slices around a wheel. Each ceremonial unit followed the same basic principle. A raised circular patio defined the outer boundary, a stepped altar or pyramid occupied the center, and a circular banquette supported a series of surrounding platforms. These platforms could number from 4 to 16, yet they were positioned so that the entire complex continued to radiate from a single geometric center. The scale makes this more than an unusual artistic choice. Circle 1, the largest known ceremonial ring at the site, has an estimated overall diameter of about 120 meters and originally supported 12 surrounding platforms. Radiocarbon and ceramic evidence place its construction between approximately 160 and 40 BCE. Circle 2, built later, measures about 100 meters across and contains 10 platforms arranged around its central monument. At that diameter, even a small error made while marking the original center would have spread outward through every later stage of construction. A shift of less than 1 degree would move the projected position of a feature at the perimeter by well over a meter. Yet the architecture retains a coherent radial order across a space wider than a modern football field. No steel measuring tape, optical level, or surveying instrument has been recovered from the site. The builders probably relied on wooden stakes, cords, sighting points, and repeated measurements, technologies that were entirely capable of producing accurate circles when used by trained specialists. The mystery is therefore not whether such geometry was physically possible, but how the procedure was controlled across dozens of construction stages and thousands of workers. To establish a circle of this size, the surveyors first had to select a fixed center, maintain a nearly constant radius while moving across uneven ground, and divide the circumference into carefully planned sectors. The central monument, open patio, ring-shaped bench and outer platforms then had to remain geometrically related, while each was raised from enormous quantities of earth, stone and clay. This would have been difficult enough on a flat, prepared surface, but Guachimontones stands on sloping terrain shaped by volcanic geology. Before the visible monuments could rise, builders had to create stable artificial platforms, compensate for variations in elevation, and prevent the circular plan from becoming distorted as material accumulated. Much of the architecture was not assembled from precision-cut blocks. It was formed from packed fills faced with stone and finished with plaster. That method increased the challenge because the intended shape had to be maintained during construction, rather than corrected later by trimming a finished stone surface. Architectural energetics offers a sense of the organization involved. One modern analysis estimated that completing Circle 2 may have required more than 112,000 person-days of labor spread across several construction seasons. Such a project demanded more than a gifted designer drawing a circle on the ground. Surveyors, material carriers, stoneworkers, plasterers, and separate work groups had to follow a shared plan while preserving the same center and curvature. Excavations have also identified differences between individual surrounding platforms, suggesting that separate groups may have built particular sections. If that interpretation is correct, the radial design may have functioned as both a ceremonial plan and a system for dividing labor among competing families or lineages. That possibility makes the accuracy even more revealing. The surrounding buildings are not identical, and the site is not mathematically flawless in the modern engineering sense. Variations, rebuilding, and damage are clearly present. However, the repeated circular concept survives those irregularities. Different work groups could alter the size or details of their assigned platform, but the entire ring still had to respect the central patio. The geometry appears to have controlled social space. Every platform faced inward. Every participant looked toward the same center, and no single side dominated the ceremony in the way a frontal temple staircase would. Guachimontones was also not an isolated experiment. Surveys have identified circular ceremonial complexes throughout western Mexico, with nearly 200 examples sometimes attributed to the broader Tuchitlan architectural tradition. Within the protected Guachimontones area alone, recent surveys have documented 25 circular complexes, including those belonging to the principal ceremonial centers of Los Guachimontones and Loma Alta. Their dimensions vary, but the underlying formula remains recognizable: center, altar, patio, ring, and radiating platforms. This repetition implies that the builders possessed a standardized body of geometric knowledge transmitted across settlements and generations. Exactly how that knowledge was recorded is unknown. No surviving architectural drawings explain how the circles were laid out, and the Toyquitlan tradition left no readable written account of its engineering methods. A cord tied to a central stake could generate the basic circumference, but it does not by itself explain how builders divided a vast ring into 10 or 12 sectors, corrected measurements across uneven terrain, or reproduced similar proportions at distant sites. They may have used standardized cord lengths, counting systems, and templates known only to trained specialists, but the archaeological evidence has not revealed the complete procedure. The function of the central monuments is equally uncertain. Ceramic models show tall poles rising from circular structures, sometimes with figures appearing to descend or rotate around them. This has led archaeologists to connect the buildings with pole rituals, aerial performances, fertility, rulership, or a symbolic world tree joining the earth and sky. The circular form may have represented cosmic order, the cycle of time, or the movement of wind, but none of these interpretations has been proven. Later Mesoamerican associations between circular temples and wind deities are suggestive, although applying them directly to Guachimontones risks projecting later beliefs onto an earlier society. Astronomical explanations remain even more disputed. Researchers have proposed solar, calendrical, and stellar relationships within the site, including the possibility that parts of Circle 2 encoded a 52-year Mesoamerican calendar, yet the circular plan creates many possible axes, and some apparent alignments may arise by chance or from practical decisions concerning terrain and neighboring structures. Guachimontones should therefore not be described as a confirmed astronomical machine. Its strongest evidence lies not in a speculative alignment with a distant star, but in the measurable organization of the architecture itself. That organization becomes more impressive when viewed from above. The largest rings extend for approximately 100 to 120 meters, while the central monuments, patios, and platforms remain bound to a common radial system. The builders did not need modern mathematics to accomplish this, but they did need accurate surveying traditions, disciplined labor, and a precise concept of space. Their circles are not perfect computer-generated forms, and claiming zero error would exaggerate the evidence. What survives is something more credible and perhaps more remarkable: an ancient society repeatedly controlling circular geometry at monumental scale with perishable tools that left almost no trace. Within the mountains of central Afghanistan, Bamiyan Valley once held some of the largest standing Buddhas on Earth. But behind the shattered statues lies something far stranger: a forgotten engineering complex carved directly into a cliff face, containing ancient tunnel systems, advanced pigments, and what may be the earliest oil paintings ever discovered on the planet. The world first became aware of Bamiyan through travelers along the Silk Road, but modern archaeological investigation accelerated during the 19th and 20th centuries as French, Afghan, and later Japanese teams mapped the valley's massive cliffside network. What they found was not just a religious site, it was an ancient technological achievement hidden inside a mountain. The most famous structures were the two giant Buddha statues built around the 6th century CE. One stood approximately 38 meters tall, while the larger reached nearly 55 meters, taller than many modern buildings. Unlike ordinary sculptures, these were not freestanding monuments. They were carved directly into vertical sandstone cliffs nearly 2,500 meters above sea level. Even today, engineers question how ancient builders managed construction on such dangerous surfaces without modern cranes, steel scaffolding, or powered lifting systems. The statues themselves were only the visible exterior of a much larger complex. Behind and around them, archaeologists discovered hundreds of interconnected caves, tunnels, stairways, meditation chambers, and hidden galleries carved into the rock. Estimates suggest the valley contains between 700 and 1,000 artificial caves. Many are linked by internal passage systems that allowed movement through the cliff without exposure to the outside environment. What makes Bamiyan extraordinary is that these caves do not appear random. Their spacing, alignment, and structural distribution suggest careful geological planning. Some chambers maintain surprisingly stable temperatures throughout the year, despite Bamiyan's brutal climate, where winters regularly fall below freezing while summers become intensely dry. Certain rooms also contain narrow ventilation shafts that naturally circulate air through pressure differences created by the mountain winds. Modern researchers compared parts of the system to passive cooling and airflow principles seen in Persian wind catchers, and even some modern eco-architecture. This raises one of Bamiyan's biggest mysteries. How did ancient builders calculate stability inside relatively soft sandstone without triggering catastrophic collapses? Unlike Petra, where many chambers are spread horizontally across wider rock faces, Bamiyan's cave systems climb vertically through steep cliffs filled with interconnected voids. Yet large portions survived for over 1,400 years despite earthquakes, erosion, freeze-thaw cycles, and warfare. Researchers analysing the remaining surfaces discovered another unexpected detail. The giant statues were not simply raw stone carvings. Their bodies were coated with mixtures of mud plaster reinforced with straw and plant fibres. Some sections included wooden armatures inserted directly into the cliff to support external layers. On top of this, artists added fine stucco details to create folds in clothing, facial structures, and decorative textures. The engineering challenge becomes almost unbelievable when considering scale alone. The larger Buddha contained surface areas equivalent to several modern houses stacked vertically. To complete it, workers would have needed enormous scaffold systems attached to unstable cliff faces at heights exceeding 50 meters. Historians estimate construction may have required decades of continuous labor, logistical coordination, and material transport through narrow mountain terrain. But the greatest mystery inside Bamiyan was hidden in darkness for centuries. In 2008, scientific analysis of murals inside several Bamiyan caves produced a discovery that shocked the art world. Researchers found clear evidence that some paintings had been created using drying oils mixed with pigments, effectively making them oil paintings. Radiocarbon dating placed several murals around the 7th century CE. That date changed everything. For generations, historians believed oil painting techniques emerged in Europe around the 15th century during the Renaissance, perfected by artists such as Jan van Eyck. Yet Bamiyan's murals predated European oil painting traditions by nearly 700 to 800 years. Laboratory examinations conducted using gas chromatography and mass spectrometry identified complex organic binders within the pigments. Scientists detected oils likely derived from walnuts or poppies mixed with natural resins and mineral colorants. Some blue pigments may have originated from lapis lazuli deposits in Afghanistan, one of the most valuable ancient minerals in the world. The sophistication of the chemistry stunned researchers. Oil-based painting is far more technically demanding than simple mineral or water-based pigments because drying oils oxidize slowly and require controlled layering techniques. Improper mixtures crack, darken, or detach over time. Yet parts of Bamiyan's murals survived more than 13 centuries in exposed cliff caves. Even more mysterious is the level of artistic refinement. Several murals show advanced shading, layered coloring, and detailed facial modeling, resembling techniques associated with Byzantine and later Renaissance traditions. Some researchers believe Bamiyan may represent a lost experimental phase in the evolution of global painting technology. The question becomes unavoidable. Where did this knowledge come from? Bamiyan sat directly on Silk Road trade routes connecting China, India, Persia, and the Mediterranean world. Merchants crossing the valley carried silk, spices, manuscripts, metals, and scientific knowledge. This made Bamiyan less of an isolated monastery and more of an international exchange center, where technologies from multiple civilizations could merge. The artistic style inside the caves reflects this fusion. Greek-influenced drapery appears beside Indian Buddhist symbolism. Persian decorative geometry blends with Central Asian motifs. Some ceiling patterns resemble Sasanian palace art, while certain human figures display facial proportions similar to Gandharan sculpture, influenced centuries earlier by Hellenistic traditions following Alexander the Great's campaigns. Because of this mixture, some historians describe Bamiyan as one of the greatest lost cultural laboratories of the ancient world. Yet much of it disappeared before researchers could fully study it. In March 2001, the Taliban destroyed the giant Buddha statues using explosives, artillery, and anti-aircraft weapons. The demolition horrified archaeologists worldwide, not only because of the cultural loss, but because scientists lost access to structural evidence that may have revealed ancient construction methods hidden inside the statues themselves. Even after the destruction, however, Bamiyan continued producing mysteries. Scans of the remaining cliff walls revealed hidden cavities and unexplored tunnel sections behind the statue niches. Some archaeologists suspect sealed chambers may still exist deeper inside the mountain. Others believe manuscripts or ritual objects could remain buried beneath collapsed debris fields created during the explosions. Modern laser mapping also showed evidence that portions of the cliff had been intentionally reshaped to reduce erosion around important chambers. Certain drainage channels appear engineered to divert seasonal water away from vulnerable mural areas. If true, this would indicate an advanced understanding of long-term geological preservation rarely associated with 6th century mountain architecture. Comparisons with sites such as Ajanta Caves and Petra only deepen the mystery. Ajanta possesses sophisticated Buddhist murals, but lacks Bamiyan's colossal vertical engineering scale. Petra demonstrates monumental rock-cut architecture, yet Bamiyan integrated sculpture, tunnels, structural reinforcement, climate adaptation, and oil-based painting technology into one interconnected system. Do you think Bamiyan was simply a religious site, or the remains of a lost technological center far more advanced than history admits? Share your thoughts in the comments below. A forgotten Maya city hidden in the humid lowlands of Tabasco, Mexico, contains one of the strangest engineering mysteries in the ancient Americas. Comalcalco was built not from giant limestone blocks like most Maya cities, but from millions of fired bricks, a construction method so unusual that some archaeologists once compared it more to ancient Roman engineering than traditional Maya architecture. In a civilization famous for stone pyramids, Comalcalco became the Maya world's impossible brick city. Even stranger, many of its walls still stand after more than 13 centuries inside one of the wettest tropical environments in Mesoamerica. Unlike cities such as Chichen Itza or Tikal, Comalcalco was located in a region with very limited building stone. The surrounding lowlands were dominated by clay-rich soil, rivers, mangroves, and tropical rainforest. Most ancient civilizations facing this problem simply built smaller settlements using wood or packed earth. But the people of Comalcalco attempted something far more ambitious. They industrialized brick production on a massive scale. Archaeologists estimate that some major structures at the site required hundreds of thousands of bricks. Many of these bricks were fired at temperatures between 700 and 900 degrees Celsius, hot enough to dramatically increase hardness and resistance to moisture. Maintaining such temperatures consistently in a humid tropical climate would have required enormous quantities of fuel and carefully controlled firing conditions. Yet the remains of large-scale kiln systems have never been fully identified. That absence has become one of the site's greatest mysteries. The engineering challenge becomes even more impressive when considering the climate itself. Tabasco receives over 2,000 millimeters of rainfall annually, in some regions far more than many famous archaeological zones in Mexico. Modern brick structures in tropical conditions often deteriorate rapidly without chemical sealants or reinforced concrete. But portions of Comalcalco's walls, stairways, and temple platforms have survived for over 1,300 years. Some structural sections still retain remarkably straight alignment, despite centuries of erosion, earthquakes, vegetation growth, and humidity. Part of that durability may come from the city's strange mortar formula. Chemical analysis revealed that the Maya builders mixed crushed oyster shells with lime and organic compounds to create an extremely resilient binding material. This shell-based mortar hardened through a calcium reaction process, somewhat comparable to hydraulic lime systems used in parts of the Roman world. Researchers have pointed out that both civilizations independently discovered ways to create water-resistant building compounds long before modern cement chemistry existed. What makes Comalcalco especially fascinating is that the Maya were never known as a brick-building civilization on this scale. Roman architecture relied heavily on standardized bricks because the empire possessed advanced logistical systems, road networks, and centralized labor organization. The Maya, by contrast, are usually associated with carved limestone monuments shaped by hand. Yet Comalcalco reveals evidence of large-scale material standardization. Thousands of bricks were produced in near-identical dimensions, suggesting organized production methods rather than isolated handmade construction. Even more mysterious are the markings carved into the bricks themselves. Over 4,000 engraved bricks have been documented at the site. Some contain glyph-like symbols, geometric signs, animal figures, handprints, or abstract marks whose meanings remain unknown. A number of archaeologists believe these markings may have functioned like production stamps, identifying work groups, artisans, or construction phases. If true, this would imply a level of labor management rarely associated with Maya cities. Some markings appear almost industrial in nature. Certain bricks carry repetitive symbols arranged in patterns that resemble batch indicators or placement codes. Similar systems appeared in ancient Mesopotamia and Roman construction centuries later, or in entirely different regions of the world. The possibility that the Maya independently developed organized production tracking systems has sparked major debate among researchers studying pre-Columbian engineering. The city's structural design also raises difficult questions. Large brick pyramids face serious load distribution problems because bricks can crack under uneven pressure far more easily than monolithic stone blocks. Modern engineers note that tall brick structures require careful balancing of weight transfer and compression forces, yet many of Comalcalco's surviving foundations still maintain stable geometry after centuries of partial collapse. This suggests the builders understood how to distribute enormous structural loads through layered brick arrangements and thick mortar cushioning. Another unresolved mystery involves the site's white stucco surfaces. Several temples and sculpted masks were coated in an exceptionally fine lime plaster that reflected sunlight intensely across the tropical landscape. Under sunlight, parts of the city may have appeared almost luminous. Microscopic analysis shows extremely smooth finishing techniques with very fine particle control. Reproducing the same finish today using only ancient tools and materials remains extremely difficult. Some researchers believe the reflective stucco may have also served thermal purposes. White mineral coatings can reduce solar heat absorption, helping structures remain cooler under intense tropical temperatures. If intentional, this would suggest the Maya at Comalcalco possessed sophisticated environmental adaptation knowledge integrated directly into architecture. Trade adds another layer to the mystery. Despite its swampy location, Comalcalco became connected to major Mesoamerican exchange networks. Archaeologists discovered obsidian from central Mexico, jade from Guatemala, marine shell artifacts, and evidence of cacao trade. Transporting these materials across dense wetlands and river systems would have required highly organized logistical routes. Some historians believe Comalcalco functioned as a major commercial gateway between the Maya world and the Gulf Coast. The cacao connection is especially important. Tabasco's climate was ideal for cacao cultivation, one of the most valuable luxury commodities in ancient Mesoamerica. Cacao beans were sometimes used almost like currency among elite trade systems. This economic importance may explain how Comalcalco funded such an enormous architectural experiment despite its difficult environment. Yet perhaps the biggest mystery remains the simplest question of all. Why did they choose fired brick in the first place? Most archaeologists argue that the lack of nearby stone forced the population to innovate, but others point out that the scale and precision of Comalcalco's brick production goes far beyond simple adaptation. Producing millions of bricks required labor coordination, fuel management, temperature control, material standardization, transportation systems, and long-term architectural planning. In many ways, it resembles a technological divergence within the Maya civilization itself, almost as though Comalcalco followed a completely different path of engineering evolution. The city reached its peak between the 6th and 9th centuries AD during the late Classic Maya period, when major urban centers across Mesoamerica were flourishing. Then, like many Maya cities, it declined and was eventually abandoned. The reasons remain uncertain. Environmental pressure, political instability, trade disruption, warfare, or resource exhaustion may all have played roles. But unlike many ruined Maya cities swallowed completely by jungle, Comalcalco left behind something unique, evidence that ancient American engineering may have been far more diverse and experimental than historians once believed. What do you think Comalcalco really was? Simply a clever adaptation to a harsh environment, or evidence of a forgotten engineering breakthrough far ahead of its time? Let us know your thoughts in the comments below. In the far north of South Africa, near the borders of Zimbabwe and Botswana, a sandstone hill rises above the dry Limpopo Valley. On its summit once stood Mapungubwe, a forgotten African kingdom that mastered gold with astonishing precision nearly 800 years ago. Long before European ships reached southern Africa, this civilization was already connected to global trade routes stretching from China to the Middle East. But the deeper archaeologists looked, the stranger Mapungubwe became. The site was officially rediscovered in 1932 by local farmer and explorer Van Graan, after stories of a hidden hill filled with ancient treasures circulated through the region. Archaeologist Leo Fouché later led the first formal excavations. What they uncovered would permanently change African archaeology. At first glance, Mapungubwe does not resemble famous ancient capitals like Machu Picchu or Petra. There are no gigantic temples or colossal statues. Yet beneath its relatively modest ruins was evidence of something many historians once believed impossible in southern Africa during the 13th century. A highly stratified kingdom with advanced metallurgy, international trade, centralized political authority, and engineering knowledge sophisticated enough to sustain thousands of people in an unforgiving environment. The first major mystery is the hill itself. Mapungubwe Hill rises roughly 30 meters above the surrounding plain, with steep natural sandstone cliffs acting almost like defensive walls. Archaeologists discovered that the ruling elite lived on the summit while commoners lived below, one of the earliest clear examples of class-based spatial separation in sub-Saharan Africa. That alone was historically shocking, but the logistics behind it are even more difficult to explain. The Limpopo Valley is semi-arid. Summer temperatures often exceed 35 degrees Celsius, and rainfall is unpredictable. Maintaining a permanent elite settlement on top of a rocky hill would have required organized food storage, controlled access to water, labor coordination, and political stability. Estimates suggest the wider Mapungubwe population may have reached between 5,000 and 10,000 people during its peak around AD 1220-1290. Supporting a population of that scale in such an environment would have been an immense engineering challenge. Yet archaeologists still have not found infrastructure proportional to the kingdom's apparent complexity. There is no massive reservoir system comparable to Roman cisterns, no extensive irrigation canals like those of Mesopotamia, no monumental hydraulic network like the Maya, The kingdom clearly functioned, but many of the systems that sustained it remain archaeologically invisible. And then there is the gold. The most famous artifact from Mapungubwe is the golden rhinoceros of Mapungubwe, a small ceremonial sculpture created around the 13th century. At first glance, it appears simple, but under closer examination, it becomes one of the most technically unsettling artifacts ever discovered in southern African archaeology. The rhinoceros was constructed using extremely thin sheets of hammered gold wrapped around a carved wooden core. To create it, artisans had to understand mining, smelting, hammering, shaping, cutting, and joining delicate metallic surfaces without tearing them apart. Even modern metalworkers acknowledge how difficult it is to consistently produce ultra-thin gold foil without advanced temperature control and highly refined techniques. Some of the gold sheets recovered at Mapungubwe are thinner than 1 millimeter. Producing material at that level requires remarkable control over force distribution during hammering. Too much pressure fractures the metal. Too little accomplishes nothing. Ancient craftsmen somehow mastered the balance. The deeper mystery is that the archaeological evidence for the industrial process behind this craftsmanship is surprisingly limited. Researchers have discovered furnaces, crucibles, slag, ironworking debris, and traces of metallurgical activity across the region. But the scale of surviving infrastructure does not seem to match the sophistication of the finished gold objects. Unlike ancient Egypt, where massive mining and smelting operations left behind extensive industrial scars, Mapungubwe's metallurgical footprint appears comparatively subtle. That creates a difficult question. How did a kingdom with relatively limited visible industrial infrastructure achieve such precision in gold production? Some researchers believe Mapungubwe's metallurgists may have used highly specialized small-scale furnaces capable of reaching temperatures above 1,000 degrees Celsius. Experimental archaeology has shown that charcoal-fired furnaces using forced air bellows can theoretically achieve these temperatures, but maintaining stable heat long enough to refine gold efficiently requires deep practical knowledge of airflow, fuel density, ore composition, and thermal behavior. This becomes even more impressive when compared to contemporary Europe. In many rural parts of 13th century Europe, goldsmithing was still concentrated among small elite workshops with limited precision tools. Yet, artisans in Mapungubwe were producing ceremonial gold objects with astonishing symmetry and delicate structural control in a region once incorrectly assumed to be technologically isolated. The gold itself also raises unresolved questions. Large quantities of gold artifacts have been recovered from elite burials, including bracelets, beads, scepters, and animal sculptures. This suggests access to a major supply network, yet no nearby gold source alone fully explains the kingdom's apparent wealth. Some archaeologists suspect Mapungubwe controlled trade corridors linking inland goldfields with the Swahili coast, turning the kingdom into a strategic redistribution center for precious metals moving toward Indian Ocean markets. And this leads directly into another mystery: global trade. Excavations at Mapungubwe uncovered glass beads from Persia, Chinese celadon pottery from the Song dynasty, imported ceramics, and other luxury goods originating thousands of kilometers away. These were not isolated curiosities. They were part of a functioning international exchange system. For imported Chinese ceramics to reach Mapungubwe in the 13th century, goods would have needed to travel across the Indian Ocean to East African trading ports, then move inland through a vast network of merchants, caravans, political alliances, and controlled trade routes. That implies organizational sophistication on a scale historians once denied existed in southern Africa before colonial contact. Mapungubwe was not isolated. It was connected to the medieval world economy. Its elites likely accumulated power by controlling cattle, ivory, gold, and long-distance commerce. Cattle were especially important. In many African societies, cattle represented wealth, status, and political authority. Archaeological evidence suggests Mapungubwe's rulers managed enormous herds despite environmental limitations. Maintaining such herds in a drought-prone region would have required advanced seasonal planning and territorial control. Then, almost suddenly, the kingdom disappeared. By around AD 1300, Mapungubwe was abandoned. There is no evidence of catastrophic warfare on the scale seen at sites destroyed by invasion, no signs of massive fire destruction, no confirmed epidemic. Instead, the kingdom appears to have declined quietly. Climate change is one major theory. Paleoclimate studies indicate southern Africa experienced increasing aridity during the late 13th century. Reduced rainfall could have destabilized agriculture and weakened cattle-based wealth systems. Another theory suggests trade routes gradually shifted northward toward the emerging power of Great Zimbabwe, which later became the dominant political center in the region. But neither explanation fully resolves the mystery. Civilizations usually leave transitional phases behind evidence of migration, adaptation, or gradual restructuring. Mapungubwe instead seems to fade with unusual silence. A kingdom sophisticated enough to produce advanced gold artifacts and participate in intercontinental trade somehow vanished while leaving behind surprisingly little explanation for how it truly functioned. What do you think was the true source of Mapungubwe's advanced gold technology, lost engineering knowledge, hidden trade networks, or something historians still haven't fully uncovered? Share your thoughts in the comments below. The desert plains of Bahrain hide one of the strangest landscapes on Earth. More than 170,000 burial mounds rise from the sand like frozen waves, stretching for kilometers in every direction. No giant temples, no massive palaces, just an endless sea of tombs built by a civilization that vanished nearly 4,000 years ago. The greatest mystery is not simply why the people of Dilmun built so many graves, but how a relatively small Bronze Age society managed to engineer and preserve one of the largest necropolises in human history under one of the harshest climates on the planet. The site known today as Dilmun Burial Mounds dates mainly between approximately 2,200 and 1,750 BCE. During the height of the Dilmun civilization, ancient Mesopotamian texts describe Dilmun as a wealthy trading kingdom positioned between Mesopotamia and the Indus Valley civilization. Sumerian records even referred to it as a paradise-like land, connected to purity and the afterlife. But unlike Egypt, where wealth was immortalized through pyramids and temples, Dilmun invested enormous resources into burial architecture spread across the landscape itself. From the air, the scale becomes almost unbelievable. Archaeologists estimate that at its peak, the necropolis covered more than 30 square kilometers. Some mound fields are so dense that individual tombs nearly touch each other. To put that into perspective, the total number of mounds in Bahrain is greater than the combined number of burial tumuli known from many ancient Mediterranean civilizations. Even more surprising is the consistency of their design. Most mounds follow an extremely standardized layout. A central stone chamber covered by layers of compacted earth and gravel, forming a circular hill ranging from 2 to 15 meters in diameter. Such uniformity suggests a level of organized labor and engineering control rarely associated with Gulf societies of the Bronze Age. The engineering problem becomes far more impressive when the environment is considered. Bahrain's desert climate experiences extreme heat, salt-heavy soil, seasonal humidity, and constant erosion from wind. Modern geologists note that exposed earthen structures in similar conditions deteriorate rapidly unless carefully stabilized. Yet thousands of dolmen mounds have survived for nearly 4 millennia. Excavations revealed that the builders did not simply pile sand over the dead. The layers were carefully compacted using different densities of gravel and soil, almost functioning like primitive geotechnical engineering. Some larger mounds even contain circular retaining walls made from limestone blocks designed to redistribute pressure and prevent collapse. This becomes especially mysterious in the so-called royal mounds, near Ali burial mounds. These structures are vastly larger than ordinary tombs, with some exceeding 50 meters in diameter and rising more than 12 meters high. Several contain multiple chambers connected by narrow passageways. Archaeologists discovered evidence of plaster coating on internal walls, as well as ventilation-like gaps that may have helped reduce humidity inside the burial chambers. The structural challenge here is enormous. Creating large hollow spaces beneath tons of compressed earth without causing cave-ins would have required a sophisticated understanding of weight distribution, even if learned purely through experimentation. Modern engineers comparing these structures to ancient Mediterranean tombs have noted similarities with corbelling techniques later used in Mycenaean Greece. However, dolmen's builders achieved stability using simpler materials and without the massive stone vault systems seen elsewhere. Some researchers argue that the people of Dolmen may have developed localized engineering knowledge specifically adapted to Bahrain's soft desert terrain. Others believe generations of trial and error slowly refined construction methods over centuries. One of the greatest unanswered questions involves logistics. Bahrain is not rich in large natural stone formations, meaning much of the limestone used for chamber construction likely had to be transported from other parts of the island. Even a modest mound could require several tons of material. Multiplied across more than 170,000 tombs, the total amount of earth and stone moved becomes staggering. Conservative estimates suggest millions of tons of material were relocated over the lifetime of the necropolis. Without wheeled transport systems comparable to later civilizations, archaeologists still debate how such an operation was sustained for centuries. Some theories suggest labor teams may have used sled-like dragging systems combined with temporary earthen ramps. Others propose that seasonal moisture in the soil may have reduced friction during transport, but no direct evidence for these systems has yet been found. What makes the mystery deeper is that the construction appears highly organized rather than improvised. The mounds are often arranged in clusters with remarkably consistent spacing. Satellite analysis has shown that many smaller mounds surround larger central tombs in patterns resembling hierarchical urban planning. This has led some scholars to believe the necropolis reflected a rigid social structure, where burial placement symbolized status and lineage. The wealth buried inside several tombs also reveals Dolmen's extraordinary international connections. Excavations uncovered carnelian beads traced to the Indus Valley, Mesopotamian pottery, copper from Oman, and shell artifacts from distant coastal regions. Chemical analysis of certain materials confirms trade routes extending over 1,000 kilometers across sea and desert. At a time when most societies remained regionally isolated, Dolmen operated as a maritime trade hub linking some of the world's earliest urban civilizations. Yet this creates another paradox. If Dolmen controlled such valuable trade networks, why did it invest so heavily in burial architecture instead of constructing monumental cities like Babylon or Memphis? Some archaeologists believe the burial landscape itself functioned as a political statement. The endless fields of tombs may have represented ancestral authority, territorial control, or spiritual legitimacy. In this interpretation, the necropolis was not separate from society, it was the center of society. Another strange detail is the apparent long-term continuity of construction. Evidence suggests the mounds were built continuously for hundreds of years, with relatively little deviation in architectural style. This level of cultural stability is unusual in ancient history, where wars, invasions, and dynastic changes often radically altered construction traditions. Bahrain, however, appears to have maintained a remarkably consistent funerary system over generations. Even the material selection raises questions. Geological studies indicate that builders deliberately chose limestone with lower porosity than surrounding rock, reducing salt absorption and improving resistance to thermal cracking. This may sound simple today, but identifying suitable stone types without modern testing implies extensive empirical knowledge of material behavior under desert conditions. Perhaps the most haunting mystery is how Dilmun disappeared. By the late 2nd millennium BCE, the civilization declined as trade routes shifted and regional powers expanded. But unlike many ancient societies, Dilmun did not leave behind colossal ruins destroyed by conquest or fire. Instead, it left behind silence and an ocean of graves stretching across the desert. What do you think the Dilmun burial mounds were truly built for simple burial grounds, symbols of power, or something far more mysterious? Share your thoughts in the comments below. Far beyond the crowded temples of Luxor, hidden beneath the burning limestone cliffs west of the Nile, lies a necropolis where some colors have survived longer than entire civilizations. Inside the Valley of the Queens, paintings more than 3,000 years old still glow with the deep blues, blood reds, and gold tones so vivid they appear almost modern. Archaeologists expected faded dust. Instead, they found walls that looked freshly painted. The deeper researchers looked, the stranger the sight became. The valley was officially explored in the early 19th century by European expeditions, but systematic excavation accelerated after the work of Ernesto Schiaparelli in 1904, when the tomb of Queen Nefertari was uncovered. Buried beneath debris and sealed chambers, the tomb revealed some of the finest surviving art in ancient Egypt. What shocked researchers was not only the beauty of the paintings, but their impossible preservation. The greatest mystery of the Valley of the Queens is not gold, mummies, or curses, it is chemistry. In the tomb of Queen Nefertari, many pigments remain astonishingly vibrant after more than 30 centuries. Modern conservation teams discovered that the walls were built in multiple engineered layers: limestone bedrock, mud plaster, fine gypsum coating, mineral pigments, and an ultra-thin protective organic layer. The structure functioned almost like a sealed laboratory environment. The famous Egyptian blue pigment remains one of the oldest synthetic pigments ever created by humans. To produce it, ancient craftsmen had to heat silica, copper compounds, calcium, and alkali materials to temperatures between 850 and 1000 degrees Celsius. That level of thermal control rivals early industrial ceramic production. Even more mysterious, modern infrared imaging revealed that Egyptian blue emits luminescence under infrared light, a property unknown to science until recent centuries. Compared with Roman frescoes in Pompeii, many of which faded or deteriorated after volcanic exposure, or medieval pigments that darkened within a few hundred years, the Valley of the Queens demonstrates chemical stability that seems centuries ahead of its era. Scientists studying the tombs also discovered that the walls absorb and release moisture extremely slowly. Salt crystallization, one of the greatest enemies of ancient art, was minimized because the tombs maintained unusually stable humidity levels. Some researchers now believe the Egyptians intentionally selected certain plaster mixtures to regulate microscopic water movement inside the walls. The mystery becomes even deeper when examining restoration damage. After the tomb of Nefertari was opened to tourism in the 20th century, rising humidity from visitors immediately began degrading the paintings. Carbon dioxide, sweat moisture, and airborne fungi started damaging surfaces that had remained stable for over 3,000 years. This revealed a disturbing truth. The tombs may have originally been engineered as perfectly balanced microclimate chambers. No one fully understands how ancient Egyptian builders achieved such environmental precision without modern chemistry, climate science, or laboratory instruments. The Valley of the Queens was carved directly into unstable limestone cliffs near ancient Thebes. Geological surveys show that many sections of the rock contain natural fractures capable of causing collapses. Yet, numerous chambers survived thousands of years with minimal structural failure. Ancient engineers appeared to understand stress distribution inside the mountain. Several chambers feature subtly curved ceilings that function similarly to load-dispersing vaults in later Roman and Gothic architecture. In some areas, workers intentionally left stone pillars untouched, creating primitive load-bearing support systems. The precision is difficult to explain. Many corridors maintain remarkably straight cuts over long underground distances despite supposedly being excavated with copper chisels and dolerite-pounding stones. Some wall surfaces are so smooth that modern archaeologists originally assumed later restoration work had modified them. Researchers also identified narrow ventilation shafts and secondary pits that may have reduced heat buildup and dust during excavation. Mining engineers have compared these systems to early underground airflow management techniques. For a civilization working in darkness with oil lamps, primitive tools, and no modern surveying equipment, the consistency of these underground structures remains deeply puzzling. Several tomb ceilings inside the Valley of the Queens contain detailed celestial imagery representing the Egyptian afterlife. But these were not simple decorations. The stars painted across the ceilings may correspond to real astronomical cycles, particularly Sirius, whose heliacal rising mark the annual Nile flood. Some Egyptologists believe the ceilings encoded calendrical information tied to agricultural cycles and religious ceremonies. The precision of certain star arrangements has generated debate for decades. Ancient Egyptians may have observed the sky continuously over centuries to maintain long-term astronomical records. What fascinates modern lighting specialists is the visual effect inside the tombs. Under weak torchlight, the deep blue pigments absorb light differently from surrounding mineral paints, causing stars to appear unusually vivid in darkness. Some researchers compare the effect to primitive immersive environmental design. In a sealed underground chamber illuminated only by flickering firelight, the ceilings may have appeared almost alive. Unlike the popular image of obvious pyramid entrances, many tombs in the Valley of the Queens were deliberately disguised. Entrances were concealed beneath rubble, plaster coatings, and natural-looking rock debris. After only a few years of desert erosion, distinguishing a tomb entrance from the surrounding cliff became nearly impossible. Some chambers include misleading side corridors, blocked passages, and concealed niches that may have confused tomb robbers. Archaeologists also found evidence that certain tombs were reopened centuries later by Egyptian officials themselves for repairs or ritual reuse. This raises a difficult question. How did they relocate hidden entrances after the landscape had naturally changed? Several historians believe the valley functioned as a controlled security complex rather than merely a burial ground. Compared with many royal tombs that were looted within generations, some chambers in the Valley of the Queens remained hidden for extraordinarily long periods. One of the least understood mysteries is the environmental stability inside the tombs. Deep chambers experience very small temperature fluctuations compared to the outside desert, where daytime temperatures can exceed 40 degrees Celsius. The surrounding limestone acts as a massive thermal buffer, absorbing heat slowly and releasing it gradually. Modern monitoring revealed that Even slight increases in visitor numbers dramatically alter humidity and carbon dioxide levels. In some areas, fungal colonies began appearing only decades after the tombs were reopened. This suggests the original environment existed in an extremely delicate equilibrium for thousands of years. Scientists now compare certain chambers to sealed archival vaults designed for long-term preservation. Yet these chambers were built over 3,000 years ago, with no electricity, no climate control systems, and no modern understanding of microbiology. The longer researchers study the valley, the more it appears that ancient Egyptian builders possessed an environmental awareness far beyond what historians once believed possible. Near the Valley of the Queens stood the workers' village of Deir el-Medina, where archaeological records revealed organized labor shifts, material management, payment systems, and strict progress tracking. This looked less like chaotic slave labor and more like a highly coordinated engineering project. Thousands of square meters of paintings, carvings, and plasterwork inside the tombs may have been completed within only a few years, requiring precise coordination between stonecutters, pigment makers, artists, and priests. Do you think the ancient Egyptian possessed engineering knowledge far beyond what modern historians currently accept? Share your thoughts in the comments below. Ancient ruins scattered across the forests of central Cambodia, about 200 kilometers north of Phnom Penh, have survived more than 13 centuries of monsoon rain, flooding, heat, and jungle invasion. Sambor Praekuk existed long before Angkor Wat and once served as one of the most important cities in Southeast Asia, a massive religious and political capital of the Chenla Kingdom during the 6th and 7th centuries. But the greatest mystery is not its age, it is the technology hidden inside its bricks. Many of these temples were built with joints so tight that almost no mortar can be seen between them, creating structures that survived longer than countless later buildings made with more advanced tools. Even today, archaeologists and material engineers still debate how these ancient builders achieved such precision in one of the harshest climates on Earth. French explorers first documented Sambor Praekuk in the 19th century during the colonial surveys of Cambodia, but dense jungle concealed much of the city for generations. Large-scale archaeological work expanded during the 20th century, revealing more than 100 temple structures spread across a vast urban landscape. Modern LiDAR scanning later uncovered roads, reservoirs, embankments, and hidden city layouts beneath the forest canopy, proving the settlement was far larger and more technologically organized than researchers once believed. The most astonishing feature of Sambor Praekuk is its brick construction. At first glance, many temple walls appear almost seamless, as if the bricks were fused together instead of stacked individually. In some sections, the joints between bricks are so thin they resemble machine-cut masonry, rather than handmade construction from the 7th century. This creates a major archaeological puzzle. Ancient Chenla builders did not possess modern steel cutting equipment, industrial kilns, or chemical cement. Yet many walls display an accuracy comparable to stonework seen in places such as Saxe Huaman or certain Roman imperial structures. Some gaps between bricks measure only a few millimeters. Even more surprising, many surfaces appear polished or blended together after construction, producing the illusion of a single continuous structure. Scientists have proposed several theories to explain this phenomenon. One theory suggests the builders used organic adhesives made from tree resin, plant sap, or sugar compounds mixed with ash and clay. Chemical traces discovered on some Southeast Asian temple bricks indicate the possible use of botanical binders. However, organic compounds normally decay quickly in humid tropical environments, making it difficult to explain how the structures remained stable for over 1,300 years. Another theory proposes that the bricks were partially ground and polished after placement, while still retaining moisture from firing. Experimental archaeology has shown that semi-fired clay bricks can sometimes be smoothed into tighter alignment before reaching full hardness. Yet reproducing the same precision consistently across massive temple walls remains extremely difficult, even for modern reconstruction teams. One of the most controversial hypotheses suggests the temples may have undergone secondary heating after assembly. In this scenario, the walls were exposed to controlled external heat that partially fused the outer brick surfaces together. Similar thermal bonding effects have been observed in some ancient kiln sites, though no conclusive evidence proves this occurred at Sambor Prey Kuk. What makes the mystery even more compelling is the survival rate of the bricks themselves. Cambodia's climate is extremely destructive to ancient materials. Average annual rainfall in central Cambodia exceeds 1,400 millimeters, while humidity levels regularly remain above 80%. Under such conditions, ordinary fired clay deteriorates rapidly through water absorption, biological growth, and thermal cracking. Yet many of Sambor Prey Kuk's bricks still retain remarkable hardness and their distinctive reddish-orange coloration. Some structures remain standing despite centuries of root penetration from enormous tropical trees. Engineers studying the material composition discovered that the clay appears unusually refined, with highly controlled particle distribution and firing consistency. Certain bricks may have been fired at temperatures approaching 900 to 1,000 degrees Celsius, significantly hotter than many earlier Southeast Asian constructions. The durability becomes even more extraordinary when compared with later historical buildings. Numerous medieval brick structures across tropical Asia collapsed within a few centuries without constant maintenance. By contrast, sections of Sambor Prey Kuk survived wars, monsoon cycles, earthquakes, and biological erosion for over 1,300 years. Some material scientists argue that the Chenla builders may have understood clay selection and thermal treatment at a level far more sophisticated than previously assumed. If true, much of that knowledge may have been lost long before modern historians began studying the region. Another major mystery lies in the city's unusual octagonal temples. Most early religious architecture across Asia relied on square or rectangular layouts because they are structurally easier to stabilize. Circular and polygonal structures require more advanced load distribution and geometric planning. But Sambor Prey Kuk contains several enormous octagonal towers among the earliest known examples in Southeast Asia. Constructing octagonal buildings on soft tropical ground presents major engineering challenges. Weight must be distributed evenly across angled walls, and any imbalance can create progressive structural collapse. Even centuries later, many medieval builders avoided large polygonal structures because of these complications. Researchers believe the Chenla architects possess surprisingly advanced geometric knowledge. Some scholars have suggested they used sophisticated rope measurement systems or modular proportional designs similar to methods later seen in Khmer architecture at Angkor Wat. The mystery becomes even greater because many octagonal towers remained upright despite centuries of flooding and soil movement. Without modern foundations or reinforced concrete, the survival of these structures remains difficult to fully explain. Most ancient civilizations carved decorative reliefs into stone because brick is fragile and prone to cracking. However, many structures at Sambor Prey Kuk feature highly detailed ornamental designs, seemingly integrated directly into the brick surfaces themselves. Researchers still debate whether these carvings were made before firing or after construction. If carved before firing, the artisans somehow predicted how much the clay would shrink during heating while preserving precise symmetry. If carved afterward, they managed to avoid large-scale cracking across brittle surfaces, something extremely difficult even with modern tools. The decorative motifs themselves are remarkably sophisticated. Floral spirals, mythical palace imagery, and intricate geometric patterns suggest a mature artistic tradition already existed centuries before the rise of Angkor. Some historians believe Sambor Prey Kuk represents the missing technological bridge between early Southeast Asian temple traditions and the later monumental achievements of the Khmer Empire. For decades, researchers believed Sambor Prey Kuk was simply a scattered religious complex hidden in the forest. Modern LiDAR technology completely transformed that understanding. Laser scanning revealed extensive urban planning buried beneath vegetation, including road systems, reservoirs, hydraulic embankments, canals, and organized settlement zones extending far beyond the visible temples. This discovery changed the historical timeline of early Cambodian civilization. Large-scale urban planning in the region may have emerged centuries earlier than previously believed. Some archaeologists now argue that Sambor Prey Kuk served as an experimental prototype for the hydraulic and urban engineering systems later perfected at Angkor. If true, the technological roots of the Khmer Empire may stretch much deeper into history than scholars once imagined. The city's disappearance is equally mysterious. Historical records from the Chenla period are fragmented and incomplete. No single catastrophe fully explains why such an advanced urban center gradually faded into the jungle. Warfare, trade shifts, environmental stress, or political transformation may all have contributed. But the silence left behind only deepened the mystery. Do you think the Chenla builders truly possessed construction technology far ahead of their time? Or is there still a hidden secret behind Sambor Prey Kuk that modern history has yet to uncover? Share your thoughts in the comments below. In the hills of northern Jordan, near the Yarmouk Valley, Abila of the Decapolis was once a thriving Roman frontier city. Today, beneath its collapsed columns and silent churches, archaeologists are uncovering evidence of engineering knowledge that should not have existed in a desert city nearly 2,000 years ago. The ruins of Abila were first systematically investigated during the 19th century, but major excavations accelerated in the 1980s when archaeologists began uncovering Byzantine churches, underground reservoirs, tunnels, and massive hydraulic systems hidden beneath layers of earthquake debris. What initially appeared to be another forgotten Roman settlement quickly turned into one of the strangest technological puzzles in the Decapolis world. One of the first mysteries involves water. Abila stood in a semi-arid region receiving roughly 300 to 500 millimeters of rainfall annually depending on climatic cycles, far too unstable to support a dense urban population without advanced water control. Yet excavations revealed a remarkably sophisticated hydraulic network carved directly into limestone bedrock. Stone channels carried water across long distances using gradients so precise that modern engineers comparing the system to Roman aqueduct standards found deviations of only a few millimeters per meter in certain surviving sections. That level of accuracy is difficult even with modern laser equipment. Ancient builders would have relied on primitive surveying tools, rope measurements, and gravity calculations. Yet the water in Abila appears to have moved with carefully controlled flow pressure, minimizing erosion while maximizing storage efficiency. More mysterious is how the entire system was layered vertically. Reservoirs at different elevations allowed the city to redirect water naturally using gravity alone, essentially creating a passive pressure management system. Similar hydraulic logic appears in the Nabatean city of Petra, where engineers mastered flash flood harvesting in the desert. But Abila's system seems optimized not only for survival, but for long-term urban stability during unpredictable drought cycles. Climate studies of the Eastern Mediterranean suggest the region experienced severe fluctuations between wetter and drier periods during late antiquity. Some researchers believe Abila's survival through these environmental shifts may have depended entirely on this hidden infrastructure beneath the city. But water engineering is only the beginning. Underneath several Byzantine structures, archaeologists discovered tunnels and underground chambers whose purpose remains unclear. Some are narrow and functional, while others open into surprisingly large subterranean spaces. The deeper investigators explored, the stranger the temperature patterns became. Even during intense Jordanian summers, temperatures inside certain chambers remain dramatically cooler than the surface above. Measurements taken in comparable underground limestone environments across the Levant show temperature reductions of 8 to 12 degrees Celsius compared to outside air. This has led some researchers to suspect that Abila may have used passive cooling technology centuries before modern climate engineering. The design resembles ancient Persian ventilation systems known as wind catchers, as well as subterranean cooling tunnels used in desert settlements across Iran. Yet Abila combined these ideas with Roman urban planning. Air appears to have circulated through elevation differences and hidden ventilation paths, creating natural airflow without mechanical assistance. If correct, the city may have functioned with an early form of environmental architecture, a built system designed not just for shelter, but for thermal regulation itself. Then came the earthquakes. The Jordan Rift Valley is one of the most seismically active regions in the Middle East. Historical records describe devastating earthquakes in 363 and 749 CE that destroyed entire cities across the Levant. Many settlements vanished permanently after these events, yet parts of Abila remained standing. Archaeologists examining fallen structures noticed something unusual about the masonry. Rather than rigidly locking stones together with excessive mortar, many foundations used tightly cut limestone blocks capable of slight movement during seismic activity. This flexibility may have absorbed vibrations instead of transferring destructive force directly into walls. The comparison that shocked many researchers was not Roman at all, but Incan. At Machu Picchu, Incan builders developed earthquake-resistant stonework by cutting massive blocks so precisely they could shift slightly without collapsing. Abila's engineering appears to follow a surprisingly similar principle despite existing on another continent over 1,000 years earlier. No direct connection existed between these civilizations, yet both may have independently discovered that rigid structures fail during earthquakes while flexible stone systems survive. Still, the most haunting mystery at Abila is not underground. It is colour. Inside the remains of Byzantine churches, archaeologists uncovered mosaic floors whose pigments remained astonishingly vivid after more than 1,500 years. Reds, blues, blacks, and gold tones survived despite centuries of humidity changes, heat exposure, mineral contamination, earthquakes, and human destruction. Modern conservation teams were stunned by the chemical durability of the materials. Scientific analysis revealed that many pigments were created using mineral compounds with extraordinary resistance to oxidation. Some tesserae contained iron-rich compounds capable of maintaining color stability over extremely long periods. Others appear to have incorporated rare trace minerals that reduced fading caused by ultraviolet radiation. Even more puzzling is the binding technology. The mortar beneath many mosaics still shows exceptional cohesion despite extreme age. In laboratory comparisons, some ancient lime-based compounds demonstrate compressive durability approaching lower-grade modern concrete after surviving over 1.5 millennia underground. Microscopic analysis suggests ancient builders may have unintentionally engineered mineral reactions similar to those now studied in self-healing Roman concrete research. But unlike ordinary Roman floors, the mosaics of Abila endured repeated seismic disasters. In some churches, sections collapsed while adjacent mosaic panels survived almost intact. This suggests the underlying support layers may have been designed to distribute stress unevenly during structural failure. In other words, the floor itself may have acted as a shock-absorbing surface. Researchers still debate whether this was intentional or simply an accidental result of layered Byzantine construction methods. Either explanation is extraordinary. The colours themselves remain another unresolved mystery. Certain blue and green shades appear chemically stable far beyond what experts expected from local mineral sources. Some scholars suspect trade networks supplied pigments from Egypt or Anatolia. Others argue local artisans possessed advanced purification techniques now lost to history. What makes this mystery unsettling is that modern restoration attempts often fail to recreate the same long-term stability. Many modern pigments fade within decades. The mosaics of Abila survived 15 centuries. And the city keeps becoming stranger. Excavations reveal that many streets were not aligned in perfect Roman grids. Instead, sections subtly shifted orientation according to terrain and prevailing wind direction. Researchers studying airflow patterns suggest these angled streets may have reduced hot desert wind intensity while improving ventilation through residential districts. This resembles principles now used in modern climate-responsive urban design. The city also reflects a collision of civilizations. Greek influence appears in architecture. Roman engineering shaped infrastructure. Nabatean hydraulic knowledge likely influenced water systems. Byzantine Christianity transformed public spaces into religious complexes filled with symbolic art. Yet Abila does not simply imitate these cultures. It merges them. Some archaeologists now describe the city as a technological hybrid zone, a place where engineering traditions from multiple civilizations fused into systems uniquely adapted to harsh environmental conditions. Ground-penetrating radar surveys suggest much of the city still remains buried. Beneath visible ruins lie large rectangular structures, hidden chambers, and additional underground passages extending far beyond excavated areas, meaning the greatest secrets of Abila may still be underground. Do you think ancient civilizations knew far more about engineering and materials than modern history admits? Share your thoughts in the comments below. Mountains of western Syria hide one of the most terrifying engineering mysteries of the medieval world. Crac des Chevaliers rises above the surrounding valleys like a stone machine built to survive forever. For more than 800 years, earthquakes destroyed nearby cities, empires vanished, and armies repeatedly attacked its walls. Yet the fortress endured, not simply because it was massive, but because many of its engineering principles appear strangely advanced even by modern standards. Although local populations had known the fortress for centuries, Crac des Chevaliers entered major archaeological and military studies during the 19th century, when European explorers began documenting its scale and preservation. What researchers discovered shocked historians. This was not merely a medieval castle. It was one of the most sophisticated military structures ever constructed before the industrial era. Expanded primarily by the Knights Hospitaller during the 12th and 13th centuries, the fortress covers nearly 3 hectares and stands more than 650 meters above sea level. Historical estimates suggest thousands of masons, engineers, laborers, and soldiers contributed to its construction across generations. But the deeper archaeologists examined the fortress, the stranger its engineering became. Most medieval fortifications relied on static defensive principles. Crac des Chevaliers appears to have operated differently. Its walls behaved less like rigid barriers and more like an adaptive structural system. The outer defensive walls reach nearly 3 meters in thickness, while inner sections become even heavier. Some towers exceed 9 meters thick at their bases. Yet despite their enormous mass, many surviving sections do not behave like completely rigid stone structures. Modern engineers studying the fortress observed several anomalies. Certain layers of stone appear to contain slight flexibility, mortar composition changes between structural zones, and impact fractures often stop spreading before catastrophic collapse occurs. This is highly unusual for a 12th century fortress. In modern earthquake engineering, rigid buildings often fail because shock waves transfer directly through continuous stone or concrete. Crack appears designed to interrupt or disperse those forces. Researchers have compared this effect to primitive seismic damping systems. The fortress also relies heavily on curved and angled surfaces instead of simple vertical walls. During medieval sieges, trebuchet projectiles weighing more than 100 kilograms could strike walls at speeds estimated between 100 and 160 kilometers per hour. Under repeated bombardment, ordinary medieval masonry should have shattered, yet crack survived centuries of attacks with surprisingly limited structural failure. The angled geometry may have redirected impact energy rather than absorbing it directly, a principle similar to modern blast-resistant military engineering. The disturbing question is not whether the fortress was strong. The real mystery is how medieval builders understood force distribution so effectively without modern mathematics, computer simulation, or material science. This is where crack des Chevaliers becomes truly difficult to explain. Syria lies near several active tectonic fault systems connected to the Dead Sea Transform Fault Zone, one of the most seismically dangerous regions in the eastern Mediterranean. Throughout history, devastating earthquakes repeatedly struck the area. The earthquake of 1170 severely damaged cities across Syria, while the massive earthquake of 1202 may have killed more than 1 million people across the eastern Mediterranean, according to some historical estimates. Later, earthquakes continued affecting the region for centuries, and yet crack survived. Not perfectly intact, but remarkably functional compared to surrounding settlements. Modern structural analysis revealed several engineering characteristics that may explain why. The fortress walls are not completely uniform. Instead of behaving as one continuous rigid mass, many sections appear compartmentalized. Internal chambers, layered stone arrangements, hidden cavities, and separated support zones may have helped disperse seismic energy before it could destroy entire structures. Some interior corridors are strangely narrow, asymmetrical, and irregular. Originally believed to be simple military passageways, newer theories suggest these spaces may have unintentionally functioned as pressure relief zones during earthquakes. Even more mysterious is the fortress mortar itself. Chemical studies of surviving materials revealed lime mixtures containing volcanic or silicate-rich compounds. In some areas, the mortar hardened similarly to hydraulic compounds used in later engineering traditions. This matters because flexibility is critical during earthquakes. If mortar becomes too brittle, stone walls crack immediately under vibration. But if mortar retains slight elasticity, structures can absorb and distribute seismic stress more effectively. Roman engineers achieved similar effects centuries earlier using pozzolana volcanic concrete in structures like the Pantheon. However, cracks builders operated in an entirely different military environment centuries later. This raises an uncomfortable possibility. Did medieval engineers independently rediscover lost seismic construction principles? Or had fragments of Roman and Byzantine engineering knowledge survived far longer than historians believed? Some scholars argue that crack evolved through generations of practical experimentation. Every siege and every earthquake may have taught builders how to reinforce weaknesses. Over centuries, the fortress slowly transformed into something resembling a giant engineered survival system rather than a simple castle. Modern finite element simulations conducted on certain surviving sections suggest some curved areas distribute stress more efficiently than later medieval fortifications built hundreds of years afterward. Perhaps the strangest detail of all is how certain damaged sections collapsed outward rather than inward. In most fortress failures, collapsing towers crush internal support systems and destroy core defensive areas. At crack, some wall geometries appear to redirect structural failure away from critical zones. That implies an understanding of controlled structural sacrifice, a principle central to modern military and earthquake-resistant engineering. Western Syria experiences intense summer heat, yet many interior chambers and side crack remain surprisingly cool even today. This effect was not accidental. The fortress incorporates vaulted ceilings, elevated ventilation shafts, narrow thermal corridors, and carefully positioned airflow channels that naturally regulate temperature. Hot air rises through upper openings, while denser cool air moves through lower passageways, creating passive circulation without mechanical assistance. Modern architects describe this as passive thermal regulation, yet crack implemented the concept centuries before industrial ventilation systems existed. Some underground chambers maintain relatively stable temperatures because of the enormous thermal mass of limestone walls. In several storage areas, temperature fluctuations remain dramatically lower than external conditions, even after centuries of exposure. This may explain how the fortress stored food supplies during prolonged sieges. Historical accounts suggest crack could support thousands of defenders for extended periods. That required more than military strength. It required environmental control, water management, food preservation, and thermal stability. In many ways, the fortress functioned like a giant stone refrigeration system powered entirely by physics. Viewed from above, Crac des Chevaliers reveals astonishing geometric precision. Defensive sightlines overlap with minimal blind spots, arrow slits align across multiple elevations, and curved towers maximize visibility while reducing exposed attack angles. This level of military geometry becomes even more remarkable considering the terrain itself. The fortress was constructed atop an uneven mountain ridge rather than a flat-engineered platform. Yet, despite the difficult landscape, its defensive symmetry remains highly organized. Some historians compare its strategic planning to Renaissance fortifications developed centuries later after gunpowder artillery transformed military architecture. But crack predates many of those engineering concepts entirely. The fortress appears to anticipate future defensive principles long before the technologies that supposedly inspired them even existed. Beneath Crac des Chevaliers lies a network of tunnels, storage chambers, water systems, and hidden passageways that remains only partially explored. Many areas are still too dangerous to excavate because of collapse risks. What makes the underground system strange is that some chambers have no obvious military purpose. They're too narrow for troop movement and too isolated for ordinary storage. Some researchers believe these spaces helped regulate temperature and airflow, while others suggest they functioned as emergency survival zones during long sieges. Even today, much of the underground network beneath the fortress remains unmapped. Do you think the builders of Crac des Chevaliers truly understood advanced engineering centuries ahead of their time? Or was this fortress the result of generations of trial and error? Share your thoughts in the comments below. Southern Iraq, near the dried marshlands of Di-Qar, hides the buried ruins of Girsu beneath layers of desert like the remains of a forgotten machine. More than 4,000 years ago, this Sumerian city controlled water, engineered climate-resistant temples, and managed one of the earliest bureaucratic systems on Earth. Yet many of its technologies remain only partially understood. Girsu was first identified in the late 19th century by French archaeologist Ernest de Sarzec after local discoveries of strange inscribed statues near the mound of Tello. Excavations quickly uncovered thousands of cuneiform tablets, massive temples, canals, and diorite sculptures so advanced that some researchers struggled to explain how Bronze Age tools could have produced them. But the greatest mystery of Girsu may not be its statues or inscriptions. It may be the fact that an ancient civilization, living in one of the harshest climates on Earth, developed engineering systems that resemble environmental technologies still used today. The city flourished around 2500–2100 BCE inside the state of Lagash. At its peak, Girsu was not a primitive settlement but a carefully organized urban center connected by canals, warehouses, temples, workshops, and administrative archives. Satellite surveys show that the surrounding region was covered with artificial waterways extending across enormous distances. Some channels were engineered with slope variations so subtle that modern archaeologists measured differences of only a few centimeters over hundreds of meters. That level of hydraulic precision is difficult even with modern surveying equipment. Without lasers, modern mathematics, or steel instruments, the Sumerians somehow created a stable irrigation network capable of controlling floodwater from the Tigris and Euphrates. If the gradient had been too steep, the canals would have eroded. Too shallow, and the water would stagnate into salt marshes. Yet many sections functioned for centuries. Researchers have compared the system to early versions of Roman hydraulic engineering developed nearly 2,000 years later. Some believe the Sumerians used water-level observation techniques combined with astronomical alignment to maintain accurate elevation measurements. Others argue the canal system evolved slowly over generations through experimentation. But no fully successful reconstruction using only Bronze Age tools has ever reproduced the same large-scale precision. Still, the canals are not the strangest part of Girsu. Among the most mysterious structures ever uncovered, there are the temple complexes dedicated to Ningirsu, especially what archaeologists sometimes describe as the White Temple structures because of their reflective outer surfaces. These buildings were constructed primarily from mud brick, one of the weakest building materials in extreme weather. Southern Iraq experiences brutal environmental conditions. Summer temperatures regularly exceed 45 degrees Celsius, while seasonal flooding and salt-rich soil rapidly destroy exposed structures. Under those conditions, ordinary mud brick should have eroded within decades. Yet parts of Girsu's sacred architecture survived for millennia. Analysis of surviving plaster and wall fragments revealed unusual mixtures of clay, gypsum, ash, crushed reeds, mineral salts, and organic compounds. Some layers appear intentionally designed to reflect solar radiation while reducing internal heat transfer. Thermal studies conducted on comparable Mesopotamian materials suggest certain reflective plasters could reduce interior temperatures by several degrees compared to untreated mud brick. This has led some researchers to compare Girsu's temple coatings to passive cooling systems seen much later in Persian desert architecture. Structures like the Yakhchals of Iran used reflective surfaces, thick insulation, airflow manipulation, and evaporative cooling to preserve ice in desert conditions. But Girsu predates many of those systems by more than 1,000 years. The unanswered question is how the Sumerians understood the thermal behavior of materials so effectively. Some temple walls were extraordinarily thick, creating thermal lag that delayed heat transfer into interior chambers. In modern architecture, similar principles are used in passive climate control systems, designed to stabilize indoor temperatures without electricity. Computer simulations of ancient thick wall construction show that heat may take many hours to penetrate dense earthen structures, meaning interiors remain cooler during the hottest parts of the day. But Girsu's builders may have gone even further. Certain excavated surfaces appear to contain microscopic crystalline structures formed through repeated heating and mineral interaction. Some specialists suspect the builders accidentally created primitive ceramic-like weatherproof coatings during firing or drying processes. Others believe the mixtures were intentionally refined after generations of experimentation with local soils and salts. No one knows exactly which formula they used. Even modern restoration teams struggle to reproduce ancient Mesopotamian plasters with identical durability under the same environmental conditions. Some experimental reconstructions cracked rapidly after exposure to heat and salt, while ancient fragments from Girsu remained stable for thousands of years underground. And the mystery deepens when examining the city's stonework. Girsu became famous for the statues of ruler Gudea, carved from imported diorite. Diorite is an extremely hard igneous rock with a moss hardness approaching 7, comparable to granite. It is notoriously difficult to shape even with iron tools. Yet the statues display smooth curves, polished surfaces, symmetrical geometry, and tiny cuneiform inscriptions carved with astonishing control. Microscopic studies of certain cuts revealed abrasion patterns consistent with quartz sand polishing and rotary drilling techniques. Experimental archaeologists attempting to replicate the carvings using copper tools found the process painfully slow. Some estimates suggest a single statue could require tens of thousands of labor hours. Yet Girsu produced many. The city also maintained one of the earliest large-scale administrative systems ever discovered. More than 30,000 cuneiform tablets from the region document grain distribution, taxation, labor assignments, livestock inventories, temple offerings, and trade logistics. Scholars often describe the archive as a proto-bureaucratic data network. The remarkable part is not simply the existence of records, but their standardization. Many tablets follow strict accounting formats with numerical systems, official seals, categorized inventories, and organized storage procedures. In effect, Girsu developed a civilization-scale information management system nearly 2 millennia before classical Greece. Some historians argue that writing itself evolved largely because societies like Girsu required increasingly sophisticated methods of resource tracking. Without centralized data management, the city's irrigation economy may have collapsed under its own complexity. And then there is the sky. Several structures in Girsu appear aligned with astronomical events connected to lunar cycles and the heliacal rising of Sirius. The Sumerians closely linked celestial movement to agriculture, flooding, and ritual calendars. Certain temple orientations deviate only slightly from predicted ancient stellar positions. This has fueled debates about whether the city used observational astronomy as part of urban planning itself. If true, Girsu may represent one of humanity's earliest examples of architecture synchronized with long-term celestial observation. Yet despite all this sophistication, the civilization eventually declined. One major theory blames soil salinization. Continuous irrigation in hot climates causes salt to accumulate near the surface, slowly poisoning farmland. Archaeological evidence suggests wheat production in southern Mesopotamia collapsed, while salt-tolerant barley became dominant. Some estimates indicate agricultural productivity may have fallen dramatically over centuries. Ironically, the same hydraulic mastery that allowed Girsu to flourish may also have contributed to its destruction. Other theories point to river migration, political fragmentation, drought cycles, or economic overcomplexity. Whatever the cause, the once powerful city faded into ruin, eventually buried beneath layers of desert sediment. Do you think Girsu was destroyed by nature, or by the very technology that once made it powerful? Share your thoughts in the comments below. On a windswept plateau nearly 1,000 meters above sea level in northern Spain, a small Celtiberian city once forced the Roman Republic into one of the longest and most humiliating wars in its history. Numancia was not protected by giant pyramids or impossible megaliths. Its greatest mystery was something far more dangerous, a level of military engineering, logistics, and metallurgy that seemed completely out of proportion for an Iron Age tribal settlement. For almost 20 years, Rome could not break it. The ruins of Numantia were identified in the 19th century after years of debate over its true location. Systematic excavations began in 1905 under German archaeologist Adolf Schulten, whose work uncovered defensive walls, streets, weapons, storage pits, and traces of one of the largest Roman siege operations ever attempted against a single city. To understand why Numantia became legendary, the scale of Rome must be understood first. By the 2nd century BCE, Rome had already defeated Carthage, conquered much of the Mediterranean, and fielded professional armies capable of engineering roads, bridges, siege towers, and massive fortifications across entire continents. Roman military discipline was so effective that most tribal settlements collapsed rapidly once surrounded, yet Numantia resisted for nearly 2 decades. Ancient Roman sources describe repeated Roman defeats, failed assaults, destroyed supply lines, and commanders humiliated by a settlement that may have contained only 4,000 to 8,000 inhabitants. Some estimates place the defending force at barely 2,000 warriors during certain periods of the conflict. That imbalance is staggering. Modern comparisons help reveal how unusual this was. It would be similar to a small, isolated mountain town repeatedly defeating offensives from the strongest military power on Earth. Rome eventually became so frustrated that it sent Scipio Aemilianus, the same commander who destroyed Carthage in 146 BCE, specifically to end the Numantine resistance once and for all. Even then, he avoided direct assault. That decision alone reveals how dangerous Numantia had become. Unlike famous ancient cities surrounded by gigantic stone walls, Numantia relied heavily on terrain optimization. The city stood on elevated ground between river valleys near the upper Duero basin. Archaeological studies show that its fortifications were integrated directly into the natural topography. Instead of relying on monument-sized walls, the defenders created narrow access corridors, steep approach angles, and layered defensive positions that forced attackers into exposed kill zones. This type of terrain warfare resembles much later military principles used in medieval hill forts and even modern mountain defense systems. Excavations revealed strategically positioned walls following slope geometry, controlled entry points, elevated observation lines, and defensive structures adapted to natural cliffs and ravines. What makes this mysterious is the sophistication of the planning. The Celtiberians were traditionally described by Roman writers as loosely organized tribal groups, yet Numantia demonstrates an advanced understanding of defensive architecture and battlefield control. Some archaeologists compare aspects of the site to Gallic hill fort engineering, but Numantia appears unusually optimized for long-term resistance. Its builders understood something critical. A fortress does not need massive walls if the landscape itself becomes the weapon. When Scipio arrived around 134 BCE, he abandoned the standard Roman approach of direct attack. Instead, he launched one of the most ambitious siege operations of the ancient world. Roman forces constructed multiple military camps, ditches, towers, wooden barriers, fortified walls, and river blockades. The encirclement stretched roughly 9 kilometers around the city. Some historians estimate the Roman force may have exceeded 50,000 soldiers and auxiliaries during parts of the campaign. That means Rome used an army potentially larger than the entire population of Numantia itself. But the real mystery is not the Roman siege. It is how Numantia survived it. Archaeological evidence suggests the inhabitants endured conditions that should have caused collapse much earlier. Excavations uncovered underground storage pits, grain reserves, and organized urban layouts suggesting highly efficient rationing systems. Researchers still debate several unresolved questions. Did Numantia possess hidden supply tunnels? Were there concealed external trade routes? Did the city develop advanced food preservation methods? How did such a small population manage resources so effectively under total isolation? Some storage structures discovered at the site indicate careful temperature control using underground chambers. Similar systems appear in other Iron Age settlements, but Numantia's apparent endurance suggests logistics far beyond what Rome expected. This transforms the story from simple warfare into something deeper, a battle of engineering, endurance, and systems management. One reason Rome struggled was because the Numantians refused to fight conventionally. Roman armies excelled in organized battlefield formations. Their strength depended on discipline, formation cohesion, and large-scale logistics. The defenders of Numantia attacked those exact weaknesses. Historical accounts describe ambush tactics, rapid raids, night attacks, supply disruption, hit-and-run warfare, and terrain manipulation. These tactics resemble modern asymmetric warfare more than traditional ancient battles. Instead of confronting Roman legions head-on, the Celtiberians forced Rome into a prolonged war of exhaustion. Some military historians argue that Numantia demonstrated an advanced understanding of strategic attrition centuries before such concepts became formalized in military theory. This is one of the most overlooked mysteries surrounding the city. Numantia may represent evidence that Iron Age tribal societies possessed far more sophisticated military intelligence than Roman sources admitted. Among all the mysteries surrounding Numantia, the most technically fascinating may be its metallurgy. Roman armies eventually adopted weapons inspired by Iberian blades. The famous Gladius Hispaniensis, one of Rome's deadliest swords, was influenced heavily by Hispano-Celtic designs developed in Iberia. This is extraordinary. Rome, the dominant military power of the ancient world, was copying weapon technology from the very people it considered barbarians. Archaeometallurgical studies suggest Celtiberian smiths achieved surprisingly high-quality steel production for the period. Analyses of surviving blades from Iberian regions reveal strong carbon distribution, flexible yet durable structures, advanced forging consistency, and an excellent balance between hardness and elasticity. In practical terms, this meant the swords could absorb impact without shattering while maintaining sharp cutting edges. That balance is extremely difficult to achieve without careful heat control. The mystery is how Celtiberian blacksmiths managed it. Iron production in the 2nd century BCE normally suffered from inconsistent furnace temperatures and impurities. Yet some Iberian weapons demonstrate metallurgical qualities far ahead of expectations for decentralized tribal societies. Several theories attempt to explain this. Unusually rich local ore deposits, inherited metallurgical traditions from earlier Mediterranean trade networks, multi-stage forging techniques, and advanced quenching and tempering methods, but no complete consensus exists. Experimental archaeologists attempting to recreate Celtiberian blades discovered that producing similar flexibility requires remarkably precise temperature management. Even small errors during forging can ruin the metal structure completely. Some reconstructed Iberian swords performed so effectively in tests that researchers compared them favorably against early Roman weapon designs. This creates an uncomfortable historical question. If Celtiberian metallurgy was this advanced, how much ancient technological knowledge has been underestimated simply because it belonged to cultures outside the major empires? Numantia may not have possessed giant monuments, but it may have possessed something even more dangerous: industrial knowledge capable of rivaling Rome itself. After months of complete encirclement, starvation finally overwhelmed Numantia in 133 BCE. Ancient accounts claim many inhabitants chose death over surrender, with some reportedly burning their possessions and parts of the city rather than becoming Roman slaves. Archaeological evidence confirms intense destruction layers across the settlement, but even here, mysteries remain. Excavations suggest multiple burn phases instead of a single fire, implying the city may have endured repeated destruction and rapid reconstruction throughout the war. Some surviving structures also reveal mixed wood and stone construction techniques that may have improved flexibility and shock absorption during attacks. Once again, Numantia appears far more technically advanced than expected for an Iron Age tribal settlement. Do you think Numantia was simply a small tribal city, or proof that ancient civilizations possessed technologies and military knowledge far beyond what history admits? Share your thoughts in the comments below. At the southern edge of Sacudia Cremada, massive stone structures have survived for more than 3,000 years on an island with limited wood, limited metal, and no written record explaining how they were built. Yet some of those structures still stand with near-perfect balance, astronomical alignment, and engineering precision that many researchers struggle to fully explain. Sacudia Cremada was identified during archaeological surveys of Menorca's Talaiotic culture, a Bronze and Iron Age civilization that occupied the Balearic Islands roughly between 1400 BCE and 123 BCE. Excavations uncovered cyclopean walls, ritual taller monuments, underground spaces, ceramic remains, and evidence of metallurgy. Unlike Egypt, Mesopotamia, or Greece, the Talaiotic people left almost no surviving written language. Their technology must therefore be reconstructed entirely from stone, ash, tools, and structural analysis. One of the most disturbing mysteries surrounding Sacudia Cremada is the engineering logic behind its enormous stone architecture. Many walls were built using cyclopean construction, giant limestone blocks stacked without mortar. Some individual stones are estimated to weigh several tons, yet they remain fitted so tightly that modern blades cannot easily slide between them. The mystery is not merely the weight of the stones, it is the stability. Menorca experiences constant coastal erosion, seasonal humidity changes, and low-level seismic activity from the western Mediterranean basin. Over 3 millennia, those environmental pressures should have destabilized poorly engineered structures. Instead, parts of Sacudia Cremada remain structurally coherent. Researchers comparing the site to Mycenaean Greece noticed a similar use of massive polygonal stonework, but the Talaiotic builders achieved this without evidence of advanced lifting cranes, iron reinforcement, or complex pulley systems. Some wall angles even appear intentionally tilted inward, distributing compressive force in ways similar to later earthquake-resistant masonry. Experimental archaeologists attempting to recreate Talaiotic transport methods discovered that moving stones across Menorca's uneven limestone terrain would require enormous manpower coordination. Yet the island's ancient population may only have numbered in the tens of thousands. This raises a difficult question. How did a relatively isolated island society organize labor and engineering with such precision? The most iconic structures at Sacudia Cremada are the taulas, giant T-shaped stone monuments unique to Menorca. A vertical monolith supports a horizontal capstone weighing multiple tons. No visible mortar, no metal clamps, no carved locking mechanisms. At first glance they appear simple, but modern structural analysis suggests otherwise. Several taulas display surprisingly accurate center of mass distribution. If the upper stone were even slightly misaligned, the entire structure would collapse under uneven stress loads. Engineers studying reconstructed force models found that friction and balance alone may have been enough to stabilize these monuments, but only if the placement precision was extremely high. That creates a serious technological mystery. The Talaiotic civilization supposedly lacked mathematical notation, precision instruments, or written engineering formulas. Yet the balancing tolerances of some talas suggest advanced practical knowledge of load transfer and weight distribution. Some archaeologists compare the talas to the trilithons at Stonehenge, but there is an important difference. Stonehenge used carved joints between stones. Many Menorcan talas appear to rely almost entirely on gravity and balance. In engineering terms, that is significantly riskier. Even stranger, certain talas seem positioned inside ritual enclosures where sound resonance behaves unusually. Acoustic studies conducted at several talaiotic sites suggest that low-frequency echoes become amplified within enclosed stone chambers. Researchers are still debating whether this effect was accidental or intentionally designed for ceremonies. Among all the unexplained technologies at Sakudia Cremada, the most difficult mystery may be metallurgy. Archaeological excavations uncovered evidence of bronze production, high-temperature ceramic firing, slag deposits, and metalworking activity. But Menorca presents a major logistical problem. It lacks the natural industrial resources normally associated with large-scale metallurgy. Bronze production requires sustained temperatures exceeding approximately 950 degrees Celsius. Certain ceramic firing processes can demand temperatures approaching or exceeding 1000 degrees Celsius. Maintaining such heat consistently is extremely difficult even for later historical societies with abundant timber resources. Ancient Menorca did not possess large forests comparable to mainland Europe. Paleo-environmental studies suggest the island's woodland resources were relatively limited, especially after centuries of human occupation. This creates a major contradiction. How could the Talaiotic people operate metalworking systems intensive enough to leave behind widespread slag and furnace remains? One theory suggests that the islanders developed highly efficient furnace architecture capable of maximizing airflow from Mediterranean coastal winds. Some reconstructed furnace experiments showed that carefully angled air channels can dramatically increase combustion temperatures without requiring massive fuel quantities. Another possibility involves charcoal optimization. Charcoal burns hotter and more efficiently than raw wood, but producing large amounts of it on a small island would risk ecological collapse. Yet archaeological evidence suggests Talaiotic societies survived for centuries without obvious signs of total environmental breakdown. This implies they may have possessed sophisticated fuel management systems far beyond what historians once assumed for Bronze Age island cultures. The chemical composition of recovered slag samples also raises questions. Some metallurgical traces indicate surprisingly stable thermal conditions during smelting. Achieving that level of consistency without bellows systems comparable to later Roman designs would have been extraordinarily difficult. Comparisons with Bronze Age metallurgy in Cyprus and Sardinia reveal another anomaly. Those regions possessed richer copper networks and stronger trade infrastructure. Menorca did not, yet the Talaiotic people still maintained functional metal production across generations. In practical terms, Sakudia Cremada represents a civilization achieving disproportionately advanced metallurgical output despite severe environmental limitations. And no one fully understands how. Several structures at Sakudia Cremada appear aligned with the solar movements and seasonal celestial events. Surveys performed at Talaiotic sites across Menorca revealed orientations that correspond to sunrise positions during solstices and equinoxes. The statistical probability of multiple ceremonial structures accidentally sharing similar astronomical alignments is surprisingly low. This becomes even more mysterious because the Talaiotic civilization left behind no surviving astronomical texts. There are no star maps, no calendars, and no mathematical records explaining how such alignments were calculated. Some researchers believe generations of naked-eye observations allowed the islanders to track celestial cycles with remarkable accuracy. Others argue the alignments may reflect ritual symbolism rather than scientific astronomy. Yet the precision itself remains difficult to dismiss. At certain times of year, sunlight enters parts of talaiotic ceremonial spaces at highly controlled angles, illuminating specific interior zones while leaving others in darkness. Similar solar effects appear in Newgrange in Ireland and Abu Simbel in Egypt, sites famous for intentional astronomical engineering. If the talaiotic builders independently developed comparable observational systems, then their scientific understanding may have been far more advanced than traditionally believed. Another technological puzzle involves hydrology. Menorca experiences long dry summers, limited freshwater availability, and irregular rainfall patterns. Despite this, talaiotic settlements like Sarkudia Kremida were positioned in ways that appear optimized for water capture and storage. Archaeologists identified sloped surfaces, drainage pathways, and terrain modifications that may have directed rainwater into collection zones. Some underground chambers may also have functioned as temperature-stable storage spaces, protecting food and water from Mediterranean heat. This suggests the talaiotic people understood local geology and seasonal environmental behavior in remarkable detail. In modern engineering language, some of these solutions resemble passive sustainability systems, technologies designed to maximize environmental efficiency without external energy sources. For a civilization with no surviving technical manuals, the sophistication is difficult to ignore. What do you think the talaiotic people truly knew about engineering and metallurgy that history has completely forgotten? Share your thoughts in the comments below. High in the mountains of Lebanon near the frozen springs of the ancient Adonis River, Fakra Temple still stands where earthquakes, snow, and time should have destroyed it centuries ago. Yet the real mystery is not the temple itself. It is the engineering buried inside the mountain around it. The ruins were documented during early European surveys of Lebanon in the 19th century, but archaeologists quickly realized Fakra as unlike most Roman sanctuaries. Massive stone blocks sat on steep mountain terrain more than 1,500 meters above sea level. Water channels had been carved directly into solid limestone. And despite Lebanon's violent seismic history, major sections of the complex remained standing with astonishing precision. Most researchers date the main Roman construction phase to the 1st and 2nd centuries AD, likely during the reign of Emperor Claudius or Nero. But many scholars suspect the site itself is older, possibly built over a sacred Phoenician sanctuary connected to the cult of Adonis, the dying and rising god associated with mountain rivers and seasonal flooding. That possibility changes everything, because it suggests Roman engineers may have inherited and expanded a far older system already adapted to the harsh Lebanese mountains. The first mystery begins with the stone itself. Fakra was constructed using enormous limestone blocks cut directly from the surrounding mountains. Some foundation stones weigh multiple tons, comparable to the lower-range megalithic blocks seen at Baalbek. But unlike Baalbek, which sits in a broad valley with easier transport access, Fakra stands on steep elevated terrain where moving heavy material becomes exponentially more difficult. Roman engineers did possess cranes powered by tread wheels capable of lifting several tons. Archaeological reconstructions suggest large Roman cranes could lift between 6 and 10 tons under ideal conditions. However, transporting such machinery into narrow mountain environments remains difficult even with modern equipment. The slope gradients near Fakra would have forced builders to create temporary roads, ramps, or sled systems across unstable terrain. What makes the mystery deeper is the absence of large-scale transport scars around the site. At Egyptian pyramid complexes, researchers can still trace remnants of hauling ramps and quarry roads. At Fakra, evidence is far more limited. Some archaeologists believe seasonal snow may actually have been used as part of the transport process. Wet limestone sledges dragged over compacted snow or mud dramatically reduce friction coefficients, a technique experimentally demonstrated in modern engineering simulations of ancient transport systems. But even if the stones could be moved uphill, another question remains unanswered. How were they positioned so precisely on uneven mountain foundations? Several surviving walls display extremely tight stone fitting with minimal mortar gaps. Lebanon sits near the Dead Sea Transform Fault System, one of the most active seismic regions in the Middle East. Historical earthquakes in 551 AD and 1202 AD devastated entire cities across the Levant. Yet parts of Fakra survived while many later structures collapsed. Researchers comparing Roman mountain architecture have noticed something unusual. Some Fakra blocks appear designed to shift slightly during seismic stress instead of rigidly resisting movement. This resembles anti-seismic behavior seen in Inca stonework at Machu Picchu, where irregular stone joints distribute energy during earthquakes. Roman concrete usually relied on pozzolanic mortar, famous for its chemical durability, but Fakra uses far more dry-fitted stone than expected. Some engineers suspect local Phoenician building traditions were combined with Roman geometry to create hybrid earthquake-resistant foundations adapted specifically for Lebanese mountain conditions. Yet the most fascinating mystery lies not in the temple walls, but in the water hidden beneath them. The mountain hydraulic system of Fakra remains one of the least understood engineering features in Roman Lebanon. The sanctuary was built near the source of the Adonis River, a water system deeply tied to ancient religious rituals. Snowmelt from Mount Lebanon flows through limestone formations before emerging as springs around the site. Ancient builders transformed this natural hydrology into a controlled engineered network. Channels were carved directly into bedrock with gradients so precise that water could travel long distances without stagnation or destructive acceleration. Modern hydraulic engineering shows that even a small error in slope angle can destabilize mountain water systems. A decline too steep causes erosion and structural damage. Too shallow, and sediment blocks the channel. At Fakra, many channels maintain remarkably consistent flow geometry despite being cut into uneven natural rock. This is extraordinary because Roman surveyors had no laser levels, satellite mapping, or digital calculations. Their primary instruments were devices like the chorobates, a long wooden leveling beam using water to establish horizontal alignment. Vitruvius described these instruments in ancient engineering texts, but applying them accurately on steep mountain terrain covered in snow and fractured limestone would have been incredibly difficult. Some channels also contain unusually smooth interior surfaces. Experimental archaeology suggests iron chisels alone would wear down rapidly against dense Lebanese limestone during prolonged excavation. This has led some researchers to suspect abrasive slurry techniques using quartz sand and water may have been employed to accelerate cutting efficiency. Even more mysterious is the integration between ritual architecture and hydraulic control. Certain basins and channels appear positioned not merely for water supply, but for ceremonial flow patterns linked to seasonal cycles. During spring snowmelt, water volume around the sanctuary increases dramatically. Ancient worshippers may have witnessed controlled flooding rituals symbolizing the death and rebirth of Adonis. This level of environmental synchronization required deep long-term observation of mountain hydrology. Builders needed to understand annual melt cycles, freeze expansion, erosion rates, and seasonal pressure variations inside limestone aquifers. In many ways, the sanctuary functioned almost like a scientific observatory disguised as a religious complex. Comparisons are often made to the Nabatean hydraulic systems at Petra, where desert engineers controlled flash floods using dams and ceramic pipelines. But Petra managed water scarcity in arid terrain. Fakra solved the opposite problem, controlling unstable mountain runoff in freezing alpine conditions. And the climate itself may be the greatest mystery of all. At 1,500 meters elevation, the site experiences snow, freeze-thaw expansion, and severe seasonal temperature shifts capable of splitting limestone apart over centuries. Modern structural geology shows that repeated freeze cycles force water into microscopic cracks where expansion gradually destroys rock integrity. Yet many Phakra stones retain sharp edges after nearly 2,000 years. Some geologists believe the builders deliberately selected unusually dense limestone layers with lower porosity. Others suspect surface finishing techniques reduced water penetration into the stone. Similar debates surround the long-term durability of Nabatean facades at Petra and certain Roman harbour structures whose mineral reactions continue strengthening over time. The unanswered question is whether ancient engineers fully understood these material properties scientifically, or whether centuries of empirical trial and error gradually produced techniques modern archaeology still cannot completely reconstruct. The true purpose of Phakra still remains unresolved. Although officially considered a Roman sanctuary, its position overlooks major mountain routes connecting the Bekaa Valley to the Lebanese coast. Some historians believe the site was not only used for rituals, but also functioned as a water control centre, seasonal observatory, and strategic mountain outpost. That makes Phakra seem more like a complex engineering system than a simple temple. Its water channels, stone joints, and foundation structures reveal an extraordinary understanding of the mountain environment. But much of that knowledge disappeared long ago into the snow-covered mountains of Lebanon. Do you think Phakra was truly just a Roman temple? Or could it have been an advanced mountain engineering system far beyond what historians currently understand? Share your thoughts in the comments below. At the southern coast of modern-day Turkey, on a narrow peninsula facing the Mediterranean, archaeologists uncovered the remains of Side ancient city, a city that should not have survived as long as it did. Excavations beginning in the late 19th century and expanding heavily after the 1947 Turkish archaeological campaigns revealed collapsed Roman theatres, submerged harbour walls, massive aqueducts, precision-cut marble temples, and infrastructure advanced enough to rival parts of Imperial Rome itself. Yet the deeper researchers dug into Side, the stranger the city became. Many of its engineering systems appear too optimized for a coastal settlement exposed to earthquakes, salt erosion, violent Mediterranean storms, and centuries of warfare. Even today, some of the technologies that allowed Side to function remain only partially understood. The first major mystery surrounding Side is its artificial harbour engineering. Ancient records describe Side as one of the busiest trade ports in Pamphylia during the 2nd century AD, capable of supporting large Roman merchant fleets. But geographically, the city sits in a highly unstable marine environment. The Mediterranean currents near the peninsula constantly deposit sediment, while seasonal storms generate strong wave impacts capable of destroying poorly designed ports within decades. Modern coastal engineers studying the underwater remains discovered that Side's harbour used curved defensive walls that redistributed wave energy instead of resisting it directly, a principle nearly identical to modern breakwater engineering. Some submerged foundation stones weigh more than 20 tons and were fitted together with extremely small tolerances despite being placed underwater nearly 2,000 years ago. More mysterious is the mortar-binding sections of the harbour. Chemical analysis found volcanic ash compounds similar to Roman pozzolanic concrete, the same material that allowed Roman ports like Caesarea Maritima to survive underwater for centuries. But the nearest major volcanic ash sources are located far from Side. Researchers estimate that transporting enough material to build the harbour would have required thousands of tons of cargo moved across the Mediterranean using ancient ships. Even more surprising, microscopic studies suggest the concrete continued strengthening over time through reactions with seawater, similar to rare mineral growth seen in modern marine concrete experiments. Some modern seawalls deteriorate within 50 years under constant salt exposure, yet parts of Side's harbour survive nearly 2 millennia. Another unexplained system lies in the city's water infrastructure. Side existed in a region with long dry seasons and limited freshwater access, yet archaeological surveys uncovered one of the most sophisticated hydraulic networks in Anatolia. The aqueduct system stretched across difficult terrain for dozens of kilometers, feeding reservoirs, baths, fountains, and private homes. Roman engineers maintained water flow using gravity alone, often with elevation differences measured in mere centimeters over long distances. A slight miscalculation would have stopped the entire system. What continues to puzzle hydrologists is the pressure regulation. Some sections crossed valleys using inverted siphon systems capable of generating enormous internal pressure. Similar Roman siphons elsewhere have failed or collapsed over time, yet portions near Side remained operational for centuries. Stone channels were lined with waterproof compounds that still resist leakage today. Laboratory studies on surviving fragments revealed crystalline mineral structures forming inside the plaster, reducing permeability over time. Modern engineers compare this effect to self-healing concrete technology currently being developed in experimental laboratories. The city's massive Roman theatre presents another engineering mystery. Built into the urban centre rather than directly against a hillside like many Greek theatres, the structure once held more than 15,000 spectators. The challenge was enormous. Roman builders had to support massive stone seating using complex vaulted substructures while also maintaining acoustic clarity. Even today, visitors standing at the stage centre can project their voice toward upper seating levels with remarkable intelligibility. Acoustic researchers studying the theatre discovered that the seating geometry amplified mid-range human vocal frequencies while suppressing portions of background wind noise from the sea. This is particularly strange because Side's coastal winds should have severely disrupted sound transmission. Instead, the curvature of the theatre appears optimized to redirect reflected sound waves toward the audience. Modern opera halls use computer simulations to achieve similar effects, yet Roman builders accomplished this through empirical experimentation alone. Compared to medieval theatres built more than 1,000 years later, Side's acoustic precision is often superior. One of the most visually striking mysteries involves the Temple of Apollo standing directly beside the Mediterranean shoreline. Coastal salt exposure is one of the most destructive forces for marble structures. Salt crystals penetrate microscopic pores, expand during temperature changes, and gradually fracture stone from within. In many ancient coastal ruins, columns collapse after centuries of erosion. Yet several columns at Side remain standing despite constant exposure to sea wind, humidity, and storms. Researchers examining the marble noticed unusual surface polishing and tool finishing techniques that may have reduced water absorption. Some stone joints are so tightly fitted that even modern restoration teams struggle to insert measuring blades between them. Structural scans also revealed metal connectors embedded inside portions of the columns, likely designed to improve flexibility during seismic activity. This is significant because southern Anatolia sits in an active earthquake region. Ancient builders at Side may have intentionally designed parts of the temple to absorb small structural movements instead of remaining completely rigid. The urban planning of Side introduces another layer of mystery. Summer temperatures in the region regularly exceed 35 degrees Celsius, yet many structures appear designed for passive cooling centuries before modern climate-responsive architecture. Narrow streets aligned with prevailing sea winds created natural ventilation corridors throughout the city. Thick limestone walls acted as thermal buffers, slowing internal temperature changes between day and night. Archaeologists found evidence that some buildings incorporated shaded courtyards and controlled airflow openings similar to systems later seen in Persian desert architecture. Thermal modelling performed on reconstructed Roman houses at Side suggests interior temperatures could remain significantly cooler than outside conditions without mechanical ventilation. In some cases, the cooling efficiency rivals passive energy housing principles used today. Another unexplained aspect of Side is the scale of its wealth. Ancient historians described the city as a major commercial and slave trading hub, but the amount of imported luxury material found during excavations suggests economic influence far beyond what its population size would predict. Coins from Egypt, Syria, Greece, and Mesopotamia have all been recovered there. Marble types used in public structures originated from multiple regions across the Eastern Mediterranean. This raises difficult logistical questions. Maintaining such trade networks required advanced maritime coordination, stable storage infrastructure, and reliable navigation systems. Some historians believe Side possessed unusually advanced shipbuilding capabilities or maritime mapping knowledge now lost to history. The city's harbour warehouses and dock systems appear optimized for high-volume cargo turnover, similar to later medieval trade republics like Venice, despite existing more than 1,000 years earlier. Perhaps the greatest mystery is why the city ultimately failed. Historical records mention pirate attacks, earthquakes, Arab raids, and economic decline, but archaeological evidence suggests the collapse was gradual and strangely uneven. Some districts were abandoned while others remained active. Construction projects appear frozen mid-development, as though labour or resources suddenly disappeared. Environmental studies indicate that sediment slowly choked the harbour over centuries. Once the port became difficult to access, Side's economy may have collapsed from within. Yet this creates a final paradox. The same civilization capable of building advanced hydraulic systems, marine engineering, and earthquake-resistant structures could not stop the slow destruction of its harbour, the very heart of the city itself. Do you think the engineers of Side truly understood technologies far ahead of their time? Or are we still underestimating how advanced ancient civilizations really were? Share your thoughts in the comments below. Built beside one of the most dangerous geological fracture zones in the Middle East, archaeological site of Pella survived for more than 6,000 years despite earthquakes, extreme heat, floods, and repeated societal collapse. Located in the Jordan Valley, roughly 130 kilometers north of Amman, and close to the Jordan Rift Valley fault system, the city was destroyed and rebuilt over and over again across multiple civilizations. Archaeologists now believe the site contains more than 20 major occupation layers stacked on top of each other, stretching from the Neolithic period to the Islamic era. But the deeper excavations went, the stranger the discoveries became. Hidden beneath the ruins were earthquake-resistant foundations, advanced hydraulic systems, unexplained high-temperature destruction layers, and building materials whose durability still puzzles engineers today. Pella was first identified in the 19th century by explorers mapping ancient Decapolis cities, but large-scale excavations only began during the 1950s and intensified under the University of Sydney in the 1970s. What archaeologists uncovered was not just another ruined city. It was evidence of an urban centre repeatedly rebuilt in one of the harshest environments in the region. Temperatures in the Jordan Valley regularly exceed 40 degrees Celsius during summer, earthquakes frequently strike the area, and water sources fluctuate dramatically across seasons. Despite this, Pella supported dense populations, agriculture, trade, temples, baths, and industrial workshops for millennia. The first major mystery emerged from the city's foundations. Many Bronze Age structures at Pella were constructed using layered building techniques that appear unusually sophisticated for their time. Excavators discovered walls built with alternating layers of stone, compacted earth, and gravel-like fill material. Modern geological analysis suggests these layers may have absorbed seismic energy during earthquakes. Engineers comparing the structures to modern anti-seismic principles noted similarities to primitive forms of base isolation, a technique now used in skyscrapers and earthquake-resistant buildings. This becomes even stranger when compared to other ancient civilizations. The polygonal stone masonry of Machu Picchu is famous for surviving earthquakes due to flexible stone joints. Japanese pagodas use central wooden columns that disperse seismic vibrations. Yet Pella developed a completely different system thousands of years earlier, using local limestone, mud brick, and layered substructures. Archaeologists still debate whether this was intentional engineering knowledge or the accidental result of centuries of rebuilding after repeated disasters. Either way, the survival rate of some structures is statistically abnormal considering the seismic history of the Jordan Rift. Another mystery lies beneath the city itself. Excavations revealed a highly organized hydraulic network running below parts of the settlement. Channels, cisterns, drainage tunnels, and underground reservoirs formed an interconnected water management system that allowed the city to survive in semi-arid conditions. Some channels maintained gradients so precise that modern surveyors measured deviations of less than a few centimeters across long distances. This level of precision raises major questions because many of these systems predate Roman engineering in the region. Water management was the difference between life and death in the Jordan Valley. Annual rainfall was inconsistent, and flash floods could destroy crops within hours. Yet pollen analysis and botanical remains show that Pella once supported olive groves, vineyards, grain cultivation, and dense urban occupation. Researchers estimate the city required hundreds of thousands of liters of water annually to sustain its population and industries. The visible springs near the site alone could not have supported such demand. This led to theories that Pella's inhabitants tapped into hidden underground aquifers using systems similar to Persian qanats. Qanats were gently sloping underground tunnels designed to transport groundwater over long distances without pumps. But unlike classical Persian qanats, no fully preserved central extraction tunnel has been discovered at Pella. Ground-penetrating radar scans have revealed anomalies beneath unexcavated sectors, suggesting entire buried hydraulic sections may still remain hidden underground. The city's destruction layers are perhaps the most controversial mystery of all. Several excavation zones contain thick ash deposits and signs of sudden catastrophic fires. In some layers, mud bricks were exposed to temperatures high enough to alter their mineral composition. Laboratory analysis identified partial vitrification in certain materials, meaning sections were heated to temperatures approaching those used in industrial kilns. The problem is that there is no clear explanation for how such temperatures were generated across wide urban areas. Unlike Pompeii, Pella had no nearby volcano capable of producing pyroclastic heat. Warfare alone also seems insufficient in some destruction phases because weapons and mass battle remains are absent in multiple burn layers. Some researchers suspect earthquake-triggered fires may have spread through densely packed mud brick structures coated with bitumen and organic plaster. Others believe large-scale industrial workshops could have contributed to uncontrollable urban firestorms. One destruction horizon dating roughly to the Late Bronze Age collapse period aligns with the broader collapse of Eastern Mediterranean civilizations around 1200 BCE. During this era, cities from Mycenaean Greece to the Hittite Empire suddenly fell apart. Pella also shows signs of abrupt abandonment during this period, but unlike many neighbouring sites, it recovered again relatively quickly. This resilience continues to confuse historians, because most urban centres in the region experienced far longer collapse phases. Another unexplained feature involves the city's climate-adaptive architecture. Streets were oriented to maximise airflow from valley winds. Houses often included internal courtyards that created passive cooling systems by circulating shaded air through narrow chambers. Thermal studies on reconstructed layouts suggest some interior spaces could remain several degrees cooler than outside temperatures even during extreme heat. This resembles principles now used in sustainable desert architecture. Researchers also found evidence that certain buildings were rebuilt directly atop earlier foundations without completely removing previous structures. At first, this seemed inefficient, but geological surveys later suggested ancient builders may have intentionally preserved older stable foundation zones because they had already proven resistant to seismic activity. In other words, the city may have functioned as a long-term experiment in structural survival, where each generation learned from earlier collapses. The durability of Pella's construction materials presents another puzzle. Some surviving mortars contain unusual combinations of ash, lime, clay minerals, and organic additives. Microscopic analysis revealed that portions of the material appear to self-seal minor fractures when exposed to moisture. Modern engineers compare this phenomenon to experimental self-healing concrete technologies currently being researched today. Roman concrete at Pantheon became famous for surviving nearly 2,000 years due to volcanic ash reactions that strengthened over time. But Pella lacked direct access to the same volcanic materials used by Roman engineers. This means local builders may have independently discovered alternative chemical mixtures capable of improving durability under stress conditions. Even more mysterious is how much of Pella still remains buried. Only portions of the site have been fully excavated. Surveys using magnetometry and subsurface imaging indicate that massive sections of the city remain hidden beneath layers of sediment deposited by floods and centuries of erosion. Entire districts may still exist underground, including industrial workshops, storage systems, and deeper occupation layers older than current excavations. Some archaeologists believe Pella's earliest phases could radically change our understanding of urban development in the southern Levant. The site already demonstrates that advanced environmental adaptation existed far earlier than previously assumed. Long before modern engineering, Pella's inhabitants may have developed practical solutions for earthquake resistance, passive cooling, flood management, and water distribution through centuries of observation and experimentation. Montreal Castle rises above southern Jordan on a lonely mountain nearly 1,300 meters above sea level, around 30 kilometers north of Petra. Today the fortress is often called Shobak Castle, but during the Crusader period it was known as Montreal, meaning Royal Mountain. It was constructed in 1115 CE by King Baldwin IV of Jerusalem to control trade routes moving between Arabia, Egypt, and the Levant. Archaeologists first began documenting the site systematically during the 19th century, but major excavations accelerated in the 20th and 21st centuries after researchers discovered that the visible ruins represented only a fraction of the fortress. Beneath the castle were hidden tunnels, giant cisterns, underground chambers, and engineering systems carved directly into the mountain itself. What shocked researchers was not simply the size of the fortress, but the sophistication of the survival technologies embedded inside it. In one of the driest regions of Jordan, medieval builders created a self-sustaining stronghold capable of surviving long sieges with minimal outside support. Even today, parts of the hydraulic system still function after almost 900 years. The greatest mystery surrounding Montreal Castle is water. The fortress stands in an environment where annual rainfall averages only around 150-200 millimeters. In such conditions, sustaining hundreds of soldiers, animals, and civilians should have been nearly impossible. Yet excavations revealed a massive network of water reservoirs carved deep into the limestone beneath the fortress. Some cisterns reached several meters in depth and were coated with waterproof lime mortar that still resists leakage centuries later. Engineers studying the plaster found unusually dense mineral compositions similar to hydraulic mortars, later seen in advanced Islamic and Roman structures. The material reduced water seepage despite constant pressure and temperature fluctuations. Researchers estimate the storage system may have held hundreds of thousands of liters of water, enough to sustain a garrison through months of siege. The scale rivals hydraulic systems found in Nabateh and Petra, despite Montreal being a military fortress rather than a trade city. The mystery becomes deeper when considering construction logistics. Every chamber had to be carved manually into hard rock at high altitude. Ventilation, drainage, and overflow control were all integrated into the design, while some channels were angled with such precision that water continued flowing efficiently despite centuries of erosion. Modern hydrologists have compared Montreal's water management to later medieval castles in Europe, yet many European fortresses built centuries afterward possessed far less efficient systems. In some ways, Montreal appears technologically ahead of its time. One of the most terrifying discoveries at Montreal Castle is the underground stairway descending deep beneath the mountain. The passage contains nearly 300 narrow stone steps cut directly into bedrock. The tunnel drops toward a hidden water source outside the main fortress walls, allowing defenders to retrieve water during siege conditions without exposing themselves to enemy attacks. The engineering difficulty of this structure is extraordinary. Archaeologists note that the staircase maintains a remarkably stable angle for long distances. Several sections include air shafts for ventilation, water runoff channels were cut into the floor, and structural niches appear to reduce collapse pressure. Creating such a tunnel with 12th century tools would have required enormous labor and precise planning. The deeper sections become extremely narrow, suggesting builders understood how to reduce stress fractures inside confined rock corridors. Some researchers compare the system to subterranean works at Petra or Derinkuyu underground city in Cappadocia. However, Montreal differs because its tunnels were integrated into an active military fortress perched on a steep mountain ridge. Even stranger, some portions of the tunnel appear older than the Crusader occupation itself. Tool marks and masonry styles differ between sections, leading to speculation that earlier Nabatean or Byzantine builders may have created the original passage centuries before the Crusaders arrived. Jordan lies near tectonically active fault systems connected to the Dead Sea Transform. Over the centuries, the region experienced multiple destructive earthquakes strong enough to destroy entire cities, yet major portions of Montreal Castle still stand. Structural surveys revealed several advanced construction techniques, including alternating large and small stone blocks to absorb vibration, flexible inner wall cores packed with rubble, foundations anchored directly into natural bedrock, and curved wall sections distributing lateral force. These methods resemble anti-seismic techniques later documented in Byzantine and even Incan architecture. Instead of relying purely on rigid mass, the builders created walls capable of dissipating energy during tremors. Scientists studying ancient seismic engineering often compare such systems to Machu Picchu or Roman fortifications in Syria. But Montreal's remote desert location makes its sophistication difficult to explain. The fortress was supposedly built rapidly for military necessity, yet parts of its structural planning appear highly specialized. Some walls also show evidence of repeated repairs using different masonry traditions, suggesting the castle evolved over centuries and possibly incorporated knowledge from Crusader, Arab, Byzantine, and local Levantine builders simultaneously. Several stone blocks within Montreal display unusually smooth cuts and tightly fitted joints. Certain surfaces appear polished beyond what historians would expect from a frontier military fortress built under harsh conditions. Archaeologists documented nearly straight incision lines, symmetrical block shaping, narrow mortar gaps, and precision-fitted corners resistant to shifting. The mystery is not that medieval builders could cut stone, but that they achieved such consistency in an isolated desert fortress with limited transport infrastructure. Some theories suggest prefabricated blocks were shaped elsewhere and transported uphill. However, hauling multi-ton limestone blocks onto a steep mountain ridge would have required massive manpower and advanced logistical coordination. Others believe the Crusaders reused older Nabatean or Roman stone foundations already present on the site. This would explain why certain sections appear far more refined than neighbouring walls. Geological analysis also found differences in weathering rates between stones, implying some materials may originate from different construction periods entirely. In 1187, after the Battle of Hattin, the armies of Saladin swept across the Crusader kingdom of Jerusalem. Most strongholds collapsed relatively quickly. Montreal did not. Historical chronicles describe a prolonged siege lasting more than a year before the fortress finally surrendered in 1189. For a remote castle isolated in the desert, such endurance is astonishing. The defenders reportedly survived despite extreme shortages and encirclement. Medieval sources even describe soldiers selling possessions for food as the siege dragged on. Yet the fortress continued resisting long after many larger Crusader strongholds had fallen. Military historians believe Montreal's survival depended on hidden water reserves, underground storage chambers, passive cooling systems inside the rock, and carefully rationed internal resources. The underground architecture likely stabilized temperatures naturally. Rock-cut chambers remain significantly cooler than the outside desert heat even today, preserving water and food far longer than surface storage alone. Some unexplored underground sections remain inaccessible because of collapse danger, meaning the fortress may still conceal undiscovered chambers or tunnels. Many archaeologists believe the visible ruins represent only part of the original complex. Satellite surveys and excavation data indicate that large sections of the upper fortress disappeared over time due to earthquakes, stone reuse, and erosion. Ancient descriptions portray Montreal as far larger than what survives today. Researchers suspect the castle once included elevated towers now destroyed, multi-level defensive terraces, additional cistern systems, and hidden communication corridors. Ground-penetrating radar detected anomalies beneath collapsed sections, suggesting buried chambers still remain unexplored. The possibility that entire portions of the fortress remain underground has fueled speculation for decades. Some historians even theorize Montreal functioned as both a military fortress and a protected treasury station controlling caravan wealth moving through the region. Do you think Montreal Castle was simply a Crusader fortress? Or could it have been built upon the lost engineering knowledge of far older civilizations? Share your theories and thoughts in the comments below.